stellar nucleosynthesis and radiometric dating.
Mystery not solved.
You're listening to Brothers of the Serpent podcast.
And welcome back, ladies and gentlemen, boys and girls, angels and demons and monsters and serpents, to Brothers of the Serpent podcast. Coming to you not live from the 10 by 10 by 10 tangent cube of science, nestled amongst the dusty bones of an ancient seabed high atop the Everest Plateau. And this is episode 181.
That's right.
First sode of the new year.
That's also right.
Is that also correct? Yeah. Somehow I got my days all mixed up. Yeah, first sode of the new year, episode 181. And we're going to be trying something a little different for this episode.
Just this once.
Just this one time. Never going to do this again.
Nope.
It's been too much work.
Number one goal of starting a podcast.
That's
as
right.
little work as possible.
As little work as possible. And so, yeah, we are joined by the Watcher. So why don't you come on, buddy, and say what's up to everybody.
How you doing, buddy?
Yeah, it's great to have you here for the first segment, like we used to.
What's up, everybody?
So what have you been
It's easy
doing?
when you tell me what to say.
Yeah. What have you been doing? You're still...
Still maintaining a concentric, super secret space orbit around El Paso.
Right. Okay.
Nice.
Geocentric orbit over El Paso. Beneath.
But definitely
Space.
glad to be here.
Been polishing up that bunker? Getting ready for the end of the world?
Well, I mean, I like to keep it comfortable. I'm not expecting any guests. People might knock at the door, but I mean, I'll let you guys in, probably.
All right. That's good. Cool. We might take you up on that.
Might need oxygen.
Yeah.
Better open up.
I saw it in a movie once. You can turn square pegs into things that'll fit in round holes, scrub the air. It'll be all right.
Hell yeah, buddy. Well, Happy New Year. Glad to have you with us.
Happy New Year, fellas. Happy New Year's to all the listeners.
Yep.
Happy New Year, everybody.
Whole snake force. And yeah, so we are recording video for this one. First segment is going to be our normal first segment, but the rest of the show after the first segment will be a presentation that I put together. So if you're listening to this in audio, which I think most of our listeners are audio listeners, you can go check out, and I'll try to make the presentation understandable to audio listeners, but there's going to be lots of cool images and stuff in the presentation. So you might want to go check out the YouTube video once that comes up. And with these video ones, History Shift is usually able to get them out within a couple of days. Sometimes it takes him a little longer if there's problems with syncing the audio, but he always gets it out pretty soon after we publish the audio version. So you can always listen to it here and then go watch it. But yeah, so look for the YouTube version for sure.
There's always syncing problems.
There's always syncing problems.
Yep.
All right. Ready for Space Weather News from spaceweather.com. Geomagnetic Storm Watch canceled. A CME expected to strike Earth on January 6th either missed or it snuck past Earth embedded in a stream of solar wind. Either way, geomagnetic storms are no longer likely, so a slight enhancement of geomagnetic unrest during the early hours of January 6th may have signaled the CME's stealthy passage. The CME, if it indeed arrived, may have declared itself in this light show over northern Canada. And there's a photograph here taken by John David McKinnon from Wood Buffalo National Park in Alberta. The auroras danced beautifully over the Salt River, he says. This made for a very peaceful and serene night. Yeah, look at that. You imagine just sitting out there watching that. These
days.
Yeah. These auroras and a few other high latitude sightings around the same time may have been sparked by the CME in combination with the high speed solar wind stream. At the time of the display, solar wind speeds were topping 600 kilometers per second, a gaseous flow unrelated to the expected storm cloud. CME, solar wind, a combination of the two, we may never know for sure. And another story here, solar prominences. The sun has been quiet for several days now. No sunspots, no flares, but it still produced some beautiful prominences, reports Ofer Gabzo of the observatory that I can't pronounce in Israel. He took this picture on the morning of January 6th, which I'm showing to Kyle right now. Those are the prominences. They're
Oh yeah, that's cool.
I don't think they're flares, but they look like big flames or geysers, basically sticking up above the body of the sun, which has been blacked out in the image. So prominences are clouds of hot plasma held above the surface of the sun by magnetic fields. The ones photographed here are almost 3 times taller than Earth itself.
Oh my God.
This scale makes them an easy target for small telescopes. To take this picture, I used a 70 millimeter ED refracting telescope and a Daystar Quark H alpha filter tuned to the red glow of solar hydrogen, says Gabzo. They looked great despite poor conditions, which was haze and a thin cloud layer. So yeah, that would be interesting to get. I'd love to be able to take some pictures like that with our telescopes.
That's insane to imagine.
Yeah, these gigantic
Yeah, that's just
arcs of plasma that are 3 times the size of our planet.
that's crazy.
So current conditions, solar wind speed is an even 500 kilometers per second, 500.0 kilometers per second. And the density is a 6.3 protons per cubic centimeter. There are 0 sunspots. So the current spotless day stretch in 2021 total is 3 days, which is 50% of this year. Neutron count right now is 8.7% plus, which is rated as high, above the space age average. And the KP index is quiet right now, but the 24-hour max was at 4, rated as unsettled, probably because of that same CME stream he was talking about earlier. So that is your space weather news for today, for this week.
Thank you, Johnson.
You're welcome, Johns.
Look out for Electric Universe.
So I have emails. Kyle has stories. We have a vote?
Yeah, I want to do the I vote emails.
Okay.
I was just looking to see, if I have a
space weather news style story.
I mean, I guess I have 2 things. I can just do a couple of headlines here. One of them is from Earth Sky News. The space weather in Proxima's vicinity dims hopes of habitable worlds. So they're looking at Proxima Centauri and the variability of that
System.
the system, and they're just like, it's
Nothing could live there.
nothing can live there. And then the next story is from Science Daily, well-known script art site, one of my favorites. The upside of volatile space weather. Robust stellar flares might not prevent life on exoplanets and could facilitate its detection. So their point is that there could be all types of like microorganisms and stuff that can survive and thrive in a very active stellar
Absolutely.
environment. And also that due to the solar flares, our instruments that are measuring like light and stuff reflecting off of these distant planets will be able to use those flares hitting those planets and causing chemical reactions and releasing gases and heat and all these things to be able to see, oh, that gas came from this gas or whatever that is a sign or a signature of biological life. So kind of like the swamp gas from Venus type of thing.
Okay, yeah.
Signatures.
You might see biological signatures because the flares
because of the flares are creating the environment on the surface of the planet to reveal it to our instruments.
Yeah.
So
I do think that,
these stories are hard to follow.
Yeah.
I find so many like that where it's like, the one that was like,
it's like no
Venus.
possible aliens here.
Venus used to be like Earth. And then it's like Earth used to be like Venus. So.
Yeah.
Yep. It's to me, I put those together all the time because it's a sign that, and I'm not making fun of these scientists.
No,
This is the scientific method, right? There are a bunch of scientists that think one way and a bunch that think the other way based on their different studies.
Yeah.
And they're putting these things out and journalists are writing about them.
Yeah.
So they're conflicting all the time, not because, and it's sort of a clue that like, we really don't understand everything that's going on, right? There's a lot of mysteries out there. So you can't just take one narrative and say, oh yeah, we've got this figured out.
Yeah.
It's just obvious that
this goes in the manual for how the universe works.
That's right.
Yeah.
It's obvious that there's, different schools of thought different ideas. So
Yeah, and
That's cool.
I think that it seems to me more and more that I would say that probably the only requirement for life is that there be energy
yeah,
nearby in some way that can be utilized by whatever that life is. And, life will figure out how to use that energy if it can. And it may not be carbon based. I mean,
well, and it's helpful to have a molecule or an atom that has a certain type of geometry that makes it really easy to like plug into a bunch of other stuff.
yeah. Yeah.
That helps.
Yeah.
Carbon.
Right. Oxygen plugs into everything.
Yeah.
Yeah.
And carbon has right, Watcher? I mean, carbon has this nice structure that makes it special.
Yeah.
Like its geometry is special, and so it can have all these interesting reactions and be stable.
Silica also has that. Like there are so many. Both. I would say that people have been talking about the possibility of silica-based life.
Yep.
It's obviously never been found or seen, but it has the same kind of, like carbon. It's a relatively light element, a simple one, and it will combine in all these interesting ways. And obviously, we know silicates make great crystalline structures. So you could have silicate-based life in certain circumstances. It might be a whole planet with, like, think of it, silicate-based life forms, both animal and plant, mobile and immobile. Imagine being on a world like that.
So like
They would be fractal in some ways. You may not even be able to see all the parts of it. You could like just walk nearby one of the crystal trees and it'd start cutting you because it's actually all the way out there. You just can't tell because it's, fractal in nature. The parts of it become so tiny that it's just invisible.
Oh man, that's cool.
Yeah.
Did you read a sci-fi story?
I've read many sci-fi stories about people going and exploring silicate-based worlds. Yeah.
That's cool. Well, I mean, don't shells, seashells and stuff? They're silica-based.
Yeah.
It's like silica and
Yeah, but imagine that
calcium and stuff.
but those are usually a protective shell around a carbon-based life form.
Yeah, but I mean, there you go. They're already utilizing it in some way.
But
It's kind of
imagine life that was not using carbon,
right.
but all of its internal processes, including its methods of metabolism and reproduction, and everything, were based in silica.
Yeah.
I mean,
Maybe they would use carbon, but they would use it to build their shell. It would be the other way around.
Yeah, they build buckyballs around themselves.
So you like have diamond shells or something. It'd be freaking cool.
Yeah, and I don't know. I've read so many great science fiction books about that. Where one of the ones I remember was the trees. There were these trees. They call them trees, but they're not. Because they're all based. The whole world was crystal, a whole bunch of crystals or whatever. But the guy is, and he has to walk around on the planet wearing this gigantic exosuit because it's so dangerous if you're not wearing anything, everything is cutting you and slicing you up or whatever, right? And things can shoot little darts made of crystal and just, So he wears this giant exosuit that's really strong. It's basically armor, and it's powered, and he's walking around this world like sort of exploring it. And he comes across this wall of trees that are crystalline. And he can't see any way around them. He goes up and down the line of these trees. They're really giant crystal formations. And he's like, okay, I'm just got to smash my way through it. So he starts using the suit to break working his way in. And then all of a sudden the suit like gets overheated and shuts down. And then it's the computer and it starts telling him all these problems, errors, giant malfunctions, blah, blah, blah. And he figures out that the trees have this built-in self-defense function where if anything starts happening to them, they all combine together and shoot a giant laser at whatever is attacking them.
I was thinking it was going to be like piezoelectric or something. He's like breaking trees and they're building up power.
They've been building up power for forever, and they basically lased his suit and just cut a huge hole in it. So,
God,
yeah.
I would be so claustrophobic. I was in a suit and then it just shut down and you're just...
Yeah, you're stuck there. Yeah, exactly. Yeah, lots of interesting science fiction stuff about silica-based life forms. Okay, emails. This one is on episode 178, and it's called Defining Free Energy from Joseph. So 178 was that was the one we did with GMA, right, on Tesla, I believe.
Okay.
Yeah. So he says, you mentioned in episode 178 that some listeners, or maybe it was the one after that, because he says that some listeners were misunderstanding what you meant when you referred to the free energy of Nikola Tesla.
Yeah.
He says, I immediately thought of the concept of free software and how that can be confusing. You may be aware of this, but there are two independent meanings of the word free as it applies to software. One is that the software distributor does not charge the user any money to use the software. And the other is that the software distributor respects the user's right to inspect, modify, and distribute the software as they see fit. That would be like, I think of that as open source.
Open source, yeah.
He says, to distinguish between these two concepts, many people refer to software as free as in beer or free as in speech. Perhaps you should create your own version of this and refer to your concept of free energy as free as in Tesla. Also, I included a low-effort meme with this email. I used the GNU image manipulation program to create the image, which is free as in speech and free as in beer. All the best, Joseph. And yeah, he's got Zahiawas. Is this a tomb? Holding a floating pyramid. But yeah, I think I don't know. I think that I think we did a pretty good job of explaining the problems we were having with the idea of free energy, and that some people, or a lot of people, seem to think of it in terms of free as do I have to pay for it, versus how I was thinking of it as if free is in terms of physics or entropy, which is an unfair way of talking about it because there is no such thing. Mm-hmm. And then we have our own concept of free lunch, which is basically something that doesn't actually exist, but when you look for it, what it means is you're looking for
low-hanging fruit.
Yeah. You know, energy that's kind of laying around that you can snag for as little work as possible, which is, again, something we really appreciate here at Snake Bros.
That's right. But yeah, I'll think on that one because I like the free as in beer thing and free as in speech. That's cool. Yeah.
All right. This one is called The Pyramid Scheme. The Pyramid Scheme Forcing You to Talk Politics. From
what?
Yeah, from Thomas. He says, Snake Bros, your recent episode on listener communications finally got me to shed my old skin and send you and the Hiss fam an email. I've listened to your show since about episode 90 and I am up to current, but I now have the beautiful luxury of getting to go back from 89 to 1, or, maybe this will get read on the show and the haters won't know what we're talking about. For the time being, I'm one of the lucky few who still gets to listen to more than one a week, which is true. Yeah. It doesn't last long, buddy. I've had this happen to me with podcasts I love, too. I start getting near the end, and I'm like, oh, my God, I'm going to have to be waiting. I can't binge this podcast anymore. You two are so real that it's honestly freeing to me. Some of my favorite episodes are when you have your family on. Snake Stash is a beauty, hockey term. I'm from Canada, eh? Thank you so much for being true to who you are and taking us all on that journey with you. Warm and fuzzies. Anyway, I came across this article, and since I know how much y'all love talking politics, I thought I'd send it your way. And yeah, I looked at it. A lot of politics. Thanks. Yeah, I read the article. I was like, okay, it's something about pyramids and ancient Egypt and a pyramid scheme, but it was like full of politics. So yeah, definitely not something we can talk about on the show. I think he's just goosing us. Also, I just heard Dr. Mary Helen Hensley talk about her work in resonance and frequency and how she uses it in healing. Thought her work may be of interest to you, as the show on frequencies in the pyramids was amazing. Love you all. Seriously. Snakes for life. P.S. Why did the snake slither across the road?
To get to the other slide?
He says, I don't know either, but I figured you guys could finish it good.
Ah.
There you go. Ciao, brethren from another Ophidian.
Hey, warm and fuzzies, buddy.
Yeah, man.
Appreciate that.
And yeah, the article, aside from all the politics, was talking about the quote-unquote pyramid scheme of ancient Egypt and how they built a civilization that lasted for thousands of years. So it was a pyramid scheme that worked.
Oh, yeah. Yes. Pyramid schemes work.
Yeah. Okay, this one is from. Well, let's just go with we'll call him Bro. I think.
All right, Bro.
Yeah, we'll call him Bro. Dear brothers, snakes, I have come to more than tolerate your show and your work with Randall Carlson as of last May. One might even say I enjoy it. A couple of items followed by a query. Perhaps you've heard of the hip and woke social scientific theory of microaggression. Well, I am formally announcing my own newer and woker theory called quantum aggression. That's right. I am quantum aggressive. I occupy both an offensive and inoffensive position simultaneously, depending on the observer, of course.
That's brilliant. Yeah.
Quantum aggressions.
That's good.
This brings me to the next item. You may have heard tell of those who identify as flat earthers. I am officially coming out of the closet as a fat earther. That's right. I believe that the earth is fat. Maybe if it weren't so fat, it wouldn't get hit by space rocks so many friggin' times. Now for my question. You gentlemen have a great interest in ancient forgotten civilizations. These civilizations were far more in tune with mysticism than our modern materialistic culture, it seems. Well, I happen to be a professional medium. I also share a passion for science. My quest since a young age to find out what is happening to me and how and why I have regular premonitions and can see very specific details of a stranger's life is what led me to science. Have you guys ever looked into the scientific controlled experiments on psychics? It may be a far cry from geology, but I believe our respective fields do intersect. The remote viewing program in your country, which was funded $20 million and lasted for 20 years between the 1970s and 80s, were some of the most well-documented and successful extrasensory perception experiments in modern history. One such experiment led the psychics to see into ancient Mars, where the psychics perceived pyramids and very tall people. Keep in mind, the key to the remote viewing experiment is that the psychics have no clues or knowledge about what the target they are seeing is. Only the scientist knows what the target is. And in the case where the scientist chose Mars in the distant past, the remote viewer/psychic described the landscape and sky and a great catastrophe. May make for a fun aside to briefly explore. Anywho, I must be on my way. Goodbye. Bro, the psychic fat earther.
Yeah, man. I think we
did talk about that. Yeah.
Yeah, that was really
The
strange.
Mars remote viewing documents. Very strange. And I also have looked into other experiments with psychics, followed Dean Radin stuff with great interest, and even looked at some of the older, pre-World War I, and then sort of between then and World War II, the stuff with the people looking into mediums and what do they call it now? They call it the spiritualist movement, I guess.
I want to make this comparison, and it's probably totally wrong, but I'm going to do it anyway.
Yeah.
This, just for the show. But the remote viewing sort of psychic stuff, as far as like looking into it for me, is kind of like the stock market. Like there's all these stockbrokers and they all, like, anybody can invest in stock, but some people are really good at doing it and winning. Most people can win sometimes, but more often than not, they'll end up failing, right? Like gambling, for example. And the people that are really good at winning sometimes win for long periods of time and then
Bam. Yeah.
fail.
Yeah.
So it's like, it's one of those things where the way I look at it is kind of like that. It's like, do I really want to like weed into there and try to find out which one of these people is like actually doing this for real, or how long were they right? And then when did they start becoming wrong? And it's just like an impossible to know thing.
Yeah.
So, but if I had a friend who was good at it, that I was just with, for years and witnessed, that would be a totally different scenario. Or if I had it myself, right?
Yeah.
But to be someone that, like, I don't know anybody that does that.
That's why the experiments in mass psychic ability are interesting to people like us, because that is like it in any given person in the test. It's not very impressive, but statistically across a large group of people, you see that it's a more than chance, and statistically it's important, and then so that's enough data for me to be like, okay, this stuff works.
Yeah.
For most of us, it barely works, but it doesn't matter.
I'm on board.
Yeah.
Right? I'm totally on board. I'm
Yeah.
not a scriptard on this. I don't know. It's one of those things where it's like, I don't know what to do with it.
Yeah.
It's very
Hard to study.
interesting.
Yeah.
Yeah. Hard to study.
Yeah.
But that's cool.
Yeah, it is, and I have, like I said, looked into a lot of the stuff. I actually read. I don't remember who wrote this, but it was a long document, like sort of like a paper, where the guy was like, "Okay, let's just look at the history of strange paranormal stuff and psychic things, and the scientific approach to it." And he just went through case after case, starting from over 100 years ago, when people were looking at, mediums and mentalists and spiritualists, and there were photographs and details of actual scientists trying to do actual scientific research by attending these seances or these medium whatever. A lot of interesting stuff, all leading all the way up to the modern times, and it was fascinating. So yeah, I have looked at it, and
then you have people like Edgar Cayce,
yeah,
which is just like, what?
Yeah,
the stuff he did was crazy,
right? And a lot of it was wrong, but so much of it was right.
So much of it was right.
Yeah. And then a lot of it is very. It reminds me, when you're reading it, it reminds me of like what you see of the prophecies in like Greek myths, where it's written in such a way to where you're like, okay, I could not have told what that was telling me until after all this stuff happened. Yeah. And then I'm like, obviously that's what it said. But then you wonder, like, am I just reading into it? Is the prophecy any good if it can't tell me what's going on in clear language beforehand? If it's presented in this prose where you're like, okay, this could mean a lot of things, or I have no idea what that means. But then after the event takes place, you're like, that's what it meant. Man, that seems to be part of the nature of it as well. So.
Yeah. How many more emails you got?
One.
All right. Well, then I'm going to talk about this one thing that I've been thinking about that's kind of off topic a little bit, but we were real close. I was thinking about the ancient tradition of like the fates or destiny, right? And just in an everyday life situation involving people I know, and just what I'm doing, I was thinking about the situation where someone grows up in a scenario, and they looking back on their past and they're like, I don't want that. I want to escape that past.
Yeah.
And so that right there almost becomes like the fates telling you your destiny. And so you spend your life like you're afraid of becoming this type of situation or scenario or type of person, and so you're basing all of your decisions on trying to avoid those things.
Yeah.
And in so doing, it's almost like you become blinded to the rational decisions, right? Which, without the fear of this becoming something you don't want to become, then you would actually make rational decisions based on what's happening right now.
Yeah.
Whereas like you get stuck in this scenario where you have this fear of being something, and so that's guiding all of your decisions, and you end up almost blindly like walking right into that situation without even realizing it, you know? And I'm just like, man, it just dawned on me that like that myth or that little scenario in the ancient traditions is a pretty common thing that happens.
Yeah, it's common.
And it's like, kind of, I guess I'm going Dave Matheson on it, right? Like this is something to teach us about ourselves.
Yeah.
And so,
I think so, yeah,
the hero of the story is told his fate, it is told his destiny, and he spends the rest of the entire story trying to avoid that, or making all these decisions to keep that from happening, and unknowingly to himself, he fucking creates the entire scenario for it to take place.
That's right. Yeah. I mean, it happens to heroes and kings.
Yeah.
All the time. They're given this, here's the destiny, and they're like, no, And then when you get to the end of the whole story, you wonder, would all of that have happened if they hadn't been told what their destiny was? Yeah. In other words, did it require the telling to make the telling take place?
I think that's the indication.
Yeah.
Like, okay, it can happen without the telling.
Yeah.
But the likelihood, it's more open-ended.
Yeah.
So I would just say, it was like when I had this realization, I'm just like, okay, this is something I want to, pass down. I want to teach like my kids, don't base your future on fears. In other words, don't make all these decisions based on fears, because that's kind of what the myth seems to be saying, because they get the fate or they get the destiny, and they don't like it. They're afraid that's what's going to happen. So the fear
that seals their fate.
That's right. The fear comes in and replaces rational thought.
Yeah. Yeah.
So I want to also encourage everybody out there, Anyway,
that's a good point.
I
guess there's a lot of ways to look at it, because that's true.
Yeah, get rid of the fear. That's first and foremost.
So
and then you're making decisions based on reality right now and rational and logical situation. Or
so two things real quick, guys.
Yeah.
Russ, you may be thinking of the Supernatural in Society, Culture, and History.
Possibly.
It's a academic paper by Dennis Waskell and Mark Eaton. And Kyle, very, very common theme. You were absolutely right. Oedipus seals that he ends up where he ends up. Yeah. But it's because of trying to avoid the thing that was prophesized.
Yeah.
There's also Sleeping Beauty.
Yep.
I mean, it's everywhere from modern to the ancient. And the reference or frame of reference I always use is a series of books called The Sword of Truth, where
that's right.
There's prophecy everywhere, and the main character is constantly yelling at everybody like, you don't know that's going to happen.
Yeah.
It hasn't happened yet. So just stop.
Yeah, and I read those books on your recommendation. I remember, I've never forgotten them. So yeah, you're right. Sword of Truth. But yeah, the other way I've looked at it, though, is there also are stories where people embrace their destiny.
Yes.
And that doesn't make the destiny not take place, right? So it's like...
Right, but again, they're not afraid of it.
Yeah, that's
and
right.
So my point is that I guess breaking it down for me is that like the fear takes the place of rational thought and reason.
They could have had
logic.
a much better life if they would have accepted it and not feared it and just went towards it as their destiny, no matter what it was.
But then the lesson isn't really shown.
That's right.
Right?
Yeah.
In that scenario. It's a different lesson.
Yeah.
I think.
And I think you're right that there are multiple lessons, because to me the lesson has always been that, the destiny is something you can't change. But fate is. The fate is the path you take.
Yeah.
Towards the destiny, whatever it is.
Yeah. Yeah.
And you can choose your fate.
Right.
Your
destiny is death, for example.
Right. Yeah. And so in your
fate is to die alone.
Yeah.
If you spend your whole life afraid you're going to die alone, then you push all of the people around you away because you just live in fear.
Yeah.
And people don't want to be around you.
Yeah. So die
it's
alone.
that self-fulfilling sort of prophecy thing.
Yeah.
That's kind of the thing I was getting at.
Yeah. Okay. Yeah. Because a lot of times in the overt or exoteric lesson seems to be like, you can't change your destiny.
Yeah.
But you're right that there are other more subtle lessons in there about fear.
And the flip side to embracing it is, again, in a way, a lesson about fear.
Yeah.
Don't be fearful.
Yeah.
Right?
I'm afraid you're right.
Touche.
All right, I got one final email here. This one, I've been saving this one for last. It's a long one, but it's a good one. This is from Jimmy, and it's called "Dark Matter and Energy Are Stupid, and Physics is Also Stupid."
I like this guy already.
Russ and Kyle. Love the podcast. It's one of the few I listen to every time right away. Man.
Hey, thanks, buddy.
I'm a 50-year-old homeschooling dad of 2. I've been trying to get my progeny into the show, but I have been talking about most of the things you cover for 2 decades now. And my kids are absolutely sick of me prattling on about magnets, the pyramids, ancient civilizations, cataclysms, precession, aliens, psychedelics, Freemasons, and the like. I've been happily lurking while avoiding the Discord snake pit. I despise typing in chat rooms and everything that accompanies it, especially the other people typing in chat rooms. Hear that, Snake Force? He hates you all. I much prefer an actual conversation, but I can lurk no more. I've got things to say, and my kids no longer listen to me. Oh, man. I've typed too much already and said very little of import, and now I feel the need to take a break and play the guitar for a while. 26 hours later. Okay, so back to typing and my original point. I've been looking into the matter of the missing mass myself, and I am convinced it has nothing to do with dark matter or energy, but is a byproduct of the acceleration of the expanding universe. Particles in an accelerator gain mass, so why not stars and galaxies and everything else? Particle physicists seem to have the need to make things overly complex, adding more and more equations to their models to prop up the original falsehood that the universe is made out of a bunch of little things banging into each other. Of course, I could be wrong as well. As soon as I start to dig into the definitions of terms in relatively simple Newtonian physics, I begin to think that none of us really know anything at all. Take the well-trod second law of motion. Force equals mass times acceleration. Or mass times energy, he says. Simple maths will allow one to solve for either force, mass, or acceleration. So you have F equals ma, m equals F divided by A, and A equals F divided by m. So force is a vector, meaning it has magnitude and direction, and is expressed as kilograms per meter per second squared. The kilogram, the mass part of this equation, was once defined as the amount of matter in 1,000 cubic centimeters of water. It has currently been redefined in relation to the Planck constant, which links the amount of energy a photon carries with the frequency of its electromagnetic wave. It has dimensions of physical action, energy multiplied by time, or momentum multiplied by distance. It is expressed as well in kilograms and meters and seconds. Acceleration is the rate of change of the velocity of an object with respect to time. It is a vector with magnitude and direction, and is expressed in meters per second squared. So, in order to properly understand force and mass or acceleration, we must be able to properly define what a meter and a second are. Before I do that, I may need to eat some eggs and maybe smoke something. I'll be back. 6 hours, 2 eggs, 1 joint, and a short nap later. So on to meters and seconds, or rather space and time, the very stuff all of these terms are floating around in. The meter is the base unit of length in the International System of Units and is defined as the length of the path traveled by light in a vacuum in 1 over 299792458 of a second.
Zeptosecond.
Obviously, one must know how long a second is in order to measure this length. So, the second is the base unit of time in the International System of Units and is defined as the duration of 9,192,631,770 cycles of the radiation corresponding to the transition between the 2 hyperfine levels of the ground state of the cesium-133 atom. There is some molecular dipole gobbledygook under the hood of this one, but the fact remains that we're measuring frequencies here. Wave frequencies, as you may know, are measured by counting the number of crests, or high points, of waves that pass a fixed point in 1 second, or some other time period based on the second. So in order to define the length of a meter, one must know the duration of a second, which is itself arrived at by measuring the length of something in meters, in a certain amount of time, in seconds. In order to define the duration of a second, one must be able to measure in meters a wavelength of radiation in a certain amount of time in seconds, which is the unit we're attempting to measure. These measurements are all used to derive other units of measurement. They are necessary to calculate the force, acceleration, and mass of any object, and we can't define what they are without using these units themselves. So, physicists state that there isn't enough matter or energy to match their models of the universe and make up dark matter and dark energy to mask the truth. We don't even know what space and time are. It's turtles and snakes all the way down. It is now 2 days after I first began this tirade, and I am completely spent. This is the most I've typed in years. Keep up the great work, from Jimmy in North Carolina.
That's great. You should type some more.
Yeah.
Yeah, that's
Fantastically put,
that's
sir.
freaking awesome. Yep. We need to measure time so that we can come up with a measurement system for space.
That was just so well done, and that's going to feed right into
Yes.
what we're going to be talking about today. So thanks so much, Jimmy.
Really great point too about the whole relativity problem, right? Something is accelerating and it's gaining mass as it accelerates.
Oh yeah, yeah.
So, but the speed of whatever is moving is relative.
Yeah.
Like,
What is
how do I know if it's accelerating or I'm accelerating, right?
Yeah.
We don't know that.
Right.
But we look out and we're like, okay, that thing's accelerating away from us. So
Away
it
from
should
us,
have a lot
relatively, yeah.
It should be gaining a lot more mass.
Yeah.
Well, it may be actually sitting still and we're accelerating, which means we're gaining mass.
Yeah.
But we're using the stuff that's close to us to figure out the energy level of matter.
Yeah.
So if we're accelerating, that's changing.
Yeah.
But anyway, looking out throughout the entire universe and everything's accelerating away from everything else, and we're like, there's too much mass out there. There's all this gravity. It's like, dude, that's a great freaking point.
It is a great point.
That's a really good point. I've never heard anybody talk about that.
Yeah.
But I'm sure these guys have corrected for all of that in their models.
Well, how do you correct for relative speeds?
Yeah, I don't
You
know.
have to. I mean, to know really. Well, I mean,
know.
I guess because it's based on the constant of light.
That's what I mean, yeah.
Yeah.
Which
So-
they
so
admit
yeah,
changes
exactly.
when it enters different mediums like water.
Exactly. It's C is what they're talking about.
C.
Yeah.
That's right.
The
Okay.
variable C. Yeah.
We're going long, folks.
Oh yes, we have a one-up box, and then we're gonna end the segment.
Oh, and I also want to say that while Russ is getting started on that, that the jelly
Oh, that's right.
is now known as Snake Force Jam in the household here. And it's really good, and Sol and Laura eat it for breakfast a lot. I'm not real big on jelly, but I have had some, and it is delicious.
That's cool.
But yeah, Sol gets up in the morning and he's like, "Mom, can we have toast with Snake Force Jam?" Snake Force Jam, dude.
All right, I'll read this note while you
Okay.
you handle the
goods.
the physical objects.
Ooh.
All right. Dear Snake Bros and Snake Mom, Merry Christmas. Where did we come from and why are we here? Some evidence suggests that things may not be as they appear. It's all right. Have a happy New Year. From Birch.
Birch.
A few items for the three of you. You have already read Seven Eves, so no book for you. Find the +2 magical item imbued with the power of the snake. And then he's got a couple of arrows here that says laser engraved with Snake Bros logo. I should have made one more pass, so it's +2 instead of a +3 item.
Which one is that? Oh. Oh, wow.
It's laser engraved, he said, so I was thinking it would be on a... I don't know.
Okay.
Is this some soap?
Yeah. But this isn't laser engraved.
No.
Maybe it's in here.
Okay.
Man,
There's
dude,
lots
this
of
is
little
a
things,
serious
yeah.
box of goodies.
Yeah. Ooh.
So we got some soap. Handmade. Natural moisturizing a soap bar from Santa Fe Mill. And these, which are... Oh, that's a pipe tool.
Yeah.
Is it?
I think so.
Yeah.
It's beautiful.
And a package of fine Mark Twain Stag Tobacconist of Santa Fe tobacco.
All right.
And it smells delish. And I actually have my pipe in here.
And a pack of American Spirits.
And
Sweet.
some beers. Rosé Bubbles, Underwood. Wait, is this beer or is this... No, this is rosé.
Wine in a can?
I guess this is wine in a can. Okay. Maybe it's sparkling. Well,
Let me see if I can figure out what he's... Is there...
And a Happy Camper IPA and a Marble Desert Fog Hazy India Pale Ale.
Man. Those
All
sound
right,
great.
buddy.
Yeah.
And since Laura, was opening this in front of me and not really in front of me, but nearby and going, "Oh, wow. Oh my God, babe. He got you beers and there's tobacco." And I was like, "Babe, why are you telling me?"
Yeah.
But anyway, I got some ice in the cooler out there, so
All right.
because I knew.
I still don't see the engraved item. Oh, is it in this
Those
box?
are earrings.
Oh, this is for Laura.
That must be for Laura. Our ears aren't pierced. But dude, thank you so much, man.
Yeah,
Merry
so
Christmas.
is it these that he's talking about? Did he make these with a...
Those are awesome.
Yeah,
dude.
these are
That looks like
beautiful.
it was a coin or something.
Yeah, it does.
It's cut out.
Yeah. Man, dude, thank you so much. See him on the video. plus 2 magical items. All right. I'm going to take a break, and then we're going to get into this presentation. Thank you, guys.
Thank you guys all so much.
Yeah.
And thank you, Birch. Merry Christmas.
Merry Christmas. Happy New Year.
Late Christmas, Happy New Year. Happy late New Year. Late.
Snacks!
And welcome back, ladies and gentlemen, Brothers of the Serpent podcast. Special episode. Russ did all the work. I am here purely for my own enjoyment. And I hope you are too. So, this is the Cosmic Rays and Radiometric Dating presentation by Snake Bro Russ. And I've got my Mark Twain loaded up in the old pipe.
All right.
So we're going to test that out for future carbon dating.
Yeah, so the first question, I'm basically I wanted to do a show that kind of went through a lot of the dating techniques that are used in archaeology and geology and other fields. Like, it's interesting how some of these techniques have been used in this is just kind of an aside, but in like art, right? How old is some piece of art? Is it authentic, right? You can use some of these techniques to date things and find out if this is a genuine, painting or whatever, or even furniture. A lot of times they're able to sometimes match the wood with other known wood because of dendrochronology. So it's interesting stuff. But we encounter it mostly here on our show in the context of archaeology and geology. And I'm really interested in knowing what these numbers mean. When you're reading something and it's like, this is dated to this date plus or minus this amount and using this technique. And you're like, okay, what does that really mean? So some of you who have listened to the entire back catalog may remember very early on, I kind of went off on a rant on this topic.
Episode 3 or something.
Yeah. So this is like an updated version of that. Updated, right?
Yeah.
And again, like I said in that first episode, why am I starting with the stars? And that's because what's really happening here with a lot of these dating techniques is it's very large energetic events in the universe that generate the things we use to date with in a lot of contexts. Not all the time. Well, actually, yes, all the time, since everything is, in the standard model is generated inside of very large energetic objects in the universe, right? So every element comes from stars, basically, or other very large objects like quasars and blazars or active galactic nuclei, which we'll get into some of that. But specifically, cosmic rays generates a lot of like with carbon dating, it's cosmic rays that generate these molecules, these radioactive molecules. So to me, it seems like you need to start with the objects that generate the cosmic rays to really understand what's going on. And that isn't necessarily the case. Like, I could probably talk about all these dating techniques and how they work without doing that. But to me, understanding the process is, in part, is about understanding the source of the objects that we're looking at.
Right. I think it's helpful. For sure.
Yes.
Yeah.
Yeah. And so this is really a two-part presentation because the first part is about stellar nucleosynthesis. So we've all seen this. This is the periodic table of elements. It's familiar to most of us. We've all encountered it at some point in schooling or whatever. And you'll notice, and so again, I want to say that a lot of you probably already know some of the stuff I'm going to go through in the beginning of this, but it's just a refresher so that we can all be on the same page when we're talking about certain things. But you'll see they've got these various numbers around here, right? Like if you're looking at these numbers, that they're telling you the atomic number, atomic mass, and the mass number. So if you see that on carbon, you see the 6. That's the atomic number. That tells you how many protons are in the nucleus. Mm-hmm. Knowing the number of protons tells you how many electrons it has because they have to be equal for it to be
stable.
Yes, for it to be electromagnetically stable, for it to not be an ion, basically.
Right.
And then the atomic mass gives you the basically the weight of the atom, and the weight is basically measuring the objects in the nucleus. So you can basically subtract the atomic number from the atomic mass to find out how many neutrons this thing has. Okay. So in this example, you see carbon, its atomic number is 6. That's how many protons it's got. You subtract that from 12, and that tells you how many neutrons it has. Now, most of these atomic mass numbers they've got a decimal with, it's like 12.011. And that's because what they're giving you is the average atomic mass of all the possible isotopes that are known based on their based on how many of them there are, right? So the ratios of isotopes. So the most common carbon is a stable one with 6 protons and 6 neutrons. Mm-hmm. But there are carbons that have more than that. So the atomic mass of the average of all carbon
is a little heavier.
Is a little bit heavier. Yeah. So back to the periodic table of elements. We'll go through that same thing here. If we're looking at hydrogen, you'll see that hydrogen has an atomic number of 1, and then it has this mass number of 1.00794. So just by knowing that, you can tell that hydrogen has 1 proton, and that's it. No neutrons. Except in some isotopic cases where it's got some neutrons, otherwise you wouldn't have that higher, that 0.00794. Right.
Okay.
But in most cases, hydrogen just has a proton and no neutrons and 1 electron. Right. Now, if we go look at helium, it's the same. You can do the same thing. Helium its atomic number is 2. Atomic mass is 4.002602.
Yeah. So it's.
So you can tell
see
that
this is like a fusion of 2 hydrogen atoms. Basically, you put 2 hydrogen atoms together and you get helium.
Yeah, except where do the neutrons come from?
The Nutriverse.
Because, that atomic number of 2 on helium and the atomic mass of 4 tells you that it's got 2 neutrons as well as the 2 protons and 2 electrons. Mm-hmm. So that's the question. Where do we get those 2 neutrons? So now this is isotopes. Isotopes are atoms that have the same number of protons but different numbers of neutrons. Okay, so having a different number of neutrons gives the atom a different mass. So that's the difference between an isotope and an ion. An isotope, like for example, carbon-14, C14, is a radioactive isotope of carbon, which normally is 12 in atomic mass. Mm-hmm. It has too many neutrons. So isotopes never have more protons because that would change it chemically because then it would have more electrons in general, right? You see what I'm saying?
Yeah, to stay neutral, basically.
Well, yeah, to stay neutral, it'd have to have more electrons.
Neutral charge.
Yeah. So if you add electrons, the electron shell is what does all the chemical bonds.
Right.
So if you have more electrons, then you're changing the chemistry. Yeah. So it would become a different element, is what I'm saying. If you add protons, it becomes a different element. Or if you subtract them. Yeah. Mm-hmm. So stable isotopes are ones that are not radioactive. There's plenty of known stable isotopes. And some of them
now, is that, forever? Or they're just not radioactive quickly? Because don't they all decay eventually?
Yeah, yes. Yeah, okay, if you're talking about over the entire possible age of the universe, there's proton decay over time. But like, for example,
so it's considered radioactive when it's decaying at a certain rate.
It's considered radioactive when, I guess it would be at a certain rate. But the rates can be enormously long. I mean, there's some of the half-lives of these the heavier radioactive things is very long, but they're
the half-life of a stable isotope of carbon would be.
It doesn't have a half-life.
Oh, okay.
Right. It's
not known.
There's no known decay rate.
Okay.
Yeah. So unstable isotopes are radioactive. Over time, they will eventually start trying to shed some of that extra mass that's in the nucleus. Sometimes that
at least at a rate that we can measure in some way.
Yeah, exactly.
Because you can have a big ball full of those, and so since there's like trillions and trillions of them in there, some of them are going to be decaying, and so you can average out.
That's right.
The number of decay, like the ones that decay, based on the total number, and you can kind of figure out what the half-life is. Okay,
exactly. And so this is what I found when I was reading about this. The instability of an unstable isotope is a result of the size of the nucleus. So in other words, if you keep cramming neutrons into a small nucleus, like let's say you've got helium and it's got 2 protons and 2 neutrons, and I just keep jamming neutrons into there, it becomes unstable because those neutrons, while neutrally, like electrically neutral, in terms of electromagnetic charge, they're also vibrating and, they have mass.
Right.
So once that nucleus becomes too heavy for that particular proton-electron group, it will want to throw those neutrons away in some form or another. And sometimes they leave in alpha particles, which is it's like a helium nucleus. 2 protons and 2 neutrons is what they call an alpha particle of radioactive decay. So like the uranium will throw off alpha particles, which are big fat. It's a clump, not just one particle. And then beta decay, it's usually losing 1 neutron, but it doesn't come out as a neutron. It goes out as other stuff. So
the neutron actually decays into other things and flies apart.
Right. Okay. So stellar nucleosynthesis, how all this stuff gets started, how that entire periodic table is generated, is what we're going to be looking at here. And the reason I want to go through some of this is because. And again, remember, this is all standard model. Basically, everything I'm going to be telling you is pure standard model physics. Nothing you couldn't find by...
Shill.
Yeah, no, I'm total shill here. Nothing you couldn't find by cramming through Wikipedia or reading... I mean, I read quite a few papers trying to find certain details about some of these processes, and sometimes I couldn't find them. But what I'm getting at here is that I think it's important to understand how the standard model looks at this stuff, because all of their dating techniques is what we use to talk about the things we like to talk about on this show. And if we're going to either accept what they say or understand how the tools work or try to question the methods, then we need to understand the processes that they are using and the theories that they are stacking their assumptions on. Okay, so that's the idea here. So
absolutely agree.
Yeah. So we're starting here with stellar nucleosynthesis. That is, I'm pretty sure, a picture of our sun when it's very, very active with sunspots. So again, back to hydrogen, the most common element. 1 proton, 1 electron. This is how it's depicted in millions and millions of textbooks.
Yeah, the billiard balls scenario.
Yeah, billiard ball scenario. But this is supposedly an actual photograph.
That's the wave function.
Yeah, a quantum picture of what it really looks like, sort of. I mean, obviously it has to be translated into visual information, but this is a hydrogen atom. So
I love that.
So you can see how it's kind of like a note or a cymatic depiction.
Yes.
And you can. It's interesting how it's showing you that nucleus is really kind of wants to stay in the middle, but it gets out there. It's not always right in the center.
There's a geometric vibrational pattern going on.
Yeah.
That's the way I always look at it.
Look at that 1 electron is making that ring.
1 electron.
Yeah, it's one electron, right?
I prefer the cloud idea. I like that better.
All right, so The simplest nucleosynthetic process is called hydrogen burning, or the proton-proton chain. So this is how hydrogen stars turn, or the lower mass stars turn hydrogen into helium. And it's not a two-step process. It's not one hydrogen equals helium. So we'll kind of go through what this is actually telling us here. Here's a bigger picture of it. So first we're starting with this. One hydrogen plus one hydrogen. And okay, let me preface this with this. These are in plasma states. According to the Standard Model, stars are in plasma states, which basically is the fourth state of matter. Once you get the heat high enough, the electrons become free, disconnected from the nuclei, okay? So what you have in a plasma state is this strange supragaseous state where the electrons are moving wherever they want, and so are the nuclei of the atoms. But they're all, when you add it all up, it's still electrically neutral in terms of charge, but the protons, or the nuclei of the atoms of the elements, and the electrons of those elements are not held together in this plasma state. The energy levels are high enough to where the electrons can go wherever they want, which is why plasma is so magnetically strong, electrically
It's
charged.
similar to the situation within conductive metals,
Yes.
except I don't think that's happening with the nucleus. But the
Right.
electrons are
can
just
move around,
cruising
yeah.
around, right?
Yeah.
Because everything is sort of, they're sharing all of these electrons, and
Yeah.
the electrons are free to move around. Whereas in other compounds, they're sort of bound or they're stuck.
Yeah.
But in this scenario, you're saying that like the nucleus is moving around too. They're all just swimming around.
Yeah.
everywhere.
So that's why this is showing what we're looking up here is one hydrogen nucleus. That's just the proton of the one hydrogen nucleus, and then another hydrogen nucleus, which is just one proton.
Right.
By the temperature and the pressure involved in this plasmatic state that it's in the star. So the temperature is so high that these things are moving. They're, the vibrations, they're jiggling, right? But it's incredibly energetic movements, and it's strong enough to overcome the fact that these are both positively charged.
Yeah.
So they get slammed into each other in this first process that I've got circled here. And two things come out of that, or three things come out of that. One is a positron, which is actually a piece of antimatter. It's the negative version of the electron, which makes it an electron with a positive charge. So that thing goes out and immediately meets some other electron and annihilates.
Yeah.
Which generates a ton of energy because both of those particles annihilate, and now you have a whole bunch more energy. The other thing that comes out, that V, is a neutrino. Now, the first thing I want to point out when you're looking at all this is you can see how what is happening here is math, but we're looking at a visual representation of it. That neutrino was discovered by somebody messing with the math and figuring out, after I go through all these calculations, I see the positron coming out over here. I see the deuterium, which is the proton with the neutron attached to it, come out over here. But there's a little bit left.
Yeah, there's something else.
Yeah. So it's called the neutrino. And it doesn't interact hardly at all. It's massless, basically, and chargeless, basically. But it's got just that little bit of remainder that was still left over in the math, and it goes flying out, which is why
it propagates some kind of wave in the medium somehow.
Yeah. But neutrinos supposedly hardly interact with anything because they have no mass and no charge, right? So they can.
So they're out of tune. Note. They
can pass through They can pass through tons of material without ever touching anything, and without ever leaving a trace. We have neutrino detectors like in the Arctic, but they have to build these thick, massive, multiple layered detectors, and then you wait for a long time, and eventually a neutrino will accidentally run into something in your detector. But that's because billions and trillions of them are passing through it all the time. You just have to wait for one to run into something by accident. Okay? But that neutrino, both of this, the positron and the neutrino, are representations of what they're doing with the math and this physics. Okay? That positron represents the positive charge of one of those protons leaving the process, which is how you end up with a neutron. You see what I'm saying there?
Say it again.
Okay. The positron is the positive charge of one of those protons.
Yeah.
That's how you end up with a neutron.
With a neutron in the helium.
That's right.
Okay, gotcha. Yeah.
Well, that's actually H2, which is a deuterium, which is a stable isotope of hydrogen that has a neutron in it.
Oh, okay, I gotcha.
Okay. So that's what we're looking at here. H1 plus H.
So that's weird. You can separate the charge from.
Yeah, but again, remember, we're talking about math, and then they're turning it into billiard balls. So really,
right.
Yeah. But yes, that charge plus a little tiny bit of mass leaves, and now you have one proton and one neutron together in a nucleus. This makes up deuterium, which is H2. Okay, hydrogen with a neutron in it. Now that, in the next step, runs into another hydrogen proton. That sends out a gamma ray. This process does.
Why?
I don't know.
So
Don't ask me.
No. Why?
another way to think of the change and the positron that leaves, if you think in terms of magnetic poles, you take massive amounts of heat and energy and you force two positive charges together, and the resultant chaos essentially forces the charge off of one particle.
Yeah. Yeah, but again, the latest, the way the physicists are looking at this, the particles they're not really billiard balls. This is just how the depictions are.
Right.
Yeah, they're little pockets of resonance.
Yeah. So that positive charge is a particular kind of spin
Right.
and a type of resonance that's leaving one of those other types of resonances. But yeah, right now I want to stick with the billiard balls because all we're trying to do is see this process and sort of grasp how it's working. So now we're at step 2, which is the deuterium and the hydrogen running into each other. They put out a gamma ray, and now you've got helium-3, which is an isotope of helium that doesn't have enough neutrons. Okay. Now, again, we're looking at math here. The gamma ray, it represents in terms of these little bitty particles, the gamma ray this is the highest level energy of the electromagnetic spectrum, light. Gamma ray is the highest frequency, most powerful type of light. Okay, so you can see that each one of these processes, the result, you get this result, but you end up putting out a whole bunch of energy while you're doing it, which is why this can be a chain reaction. Because at each step you can see that more things are being,
and that energy, like the energy that it's putting out in that gamma ray, that gamma ray is tuned to that very process that just took place.
That's right.
So if it encounters another set that's like the 2H and the 1H,
Yeah.
it's the frequency that can help create that reaction between them.
Exactly.
Because that's the way I look at it anyway in terms of resonance.
No,
right?
that's a great
it's
way to
the
put it.
frequency that makes the glass break. And
Yes,
so
that's right.
It's going to go and help the next one do it.
Yeah.
Right? Whatever.
Yes. But in brief, what you can see in this process is that each time one of these collisions happens, you get it builds a new nucleus,
Right.
But it also lets out a whole bunch of energy in the process, which means the chain reaction can continue because those little things that are flying off, like the positron, not the neutrino, and the gamma ray, and then later on the other protons, they represent a whole bunch of energy that goes back into the system that continues this process.
Right.
So now we go to the last step, which is where two of these helium-3 nuclei run into each other. And what
Put
comes
off
out
really fast moving hydrogen.
Yes. Two hydrogen protons, new hydrogen protons come out of that, and now you have regular helium, He4, 2 neutrons and 2 protons. So this is the hydrogen burning or proton-proton chain process. This is what stars spend most of their lifetime doing.
Yeah.
The low mass stars. Okay, so that's all we're going to do with that. I'm not going to go through, but there are a whole bunch of other interesting processes like this one called the carbon-nitrogen-oxygen cycle. This is what higher mass stars do to make helium and a whole bunch of other things. But you can see this is basically going around and around in a circle, and it's generating helium from hydrogen using these other carbon, oxygen, and nitrogen, running into each other and running into other things. So I'm not going to go into all of it, but you can see it's releasing gamma rays and neutrinos and positrons the whole cycle. This takes this takes a higher temperature. In other words, the star has to have a lot more
pressure.
mass. Yeah. But in the end, what it's doing is turning hydrogen into helium.
Yeah, just using bigger chunks of stuff.
And these other ones are being created also. Here's another process called the triple alpha process. This one creates carbon, helium, and beryllium.
Beryllium, yeah.
This one takes even more energy. And then there's this
Look at how nice that carbon looks. It's just so good.
flowery. Yeah. And then there's this nightmare of a process called the alpha process, this huge, ridiculous cycle that really big stars make. And this is how they get all the way down to iron. So they're making carbon and oxygen and neon and magnesium and silicon and just sulfur and argon and calcium and carbon and just all these things that I don't even know. I didn't even try to understand how this works, but this is the diagram of the alpha process cycle.
Right.
Okay. And this is usually later in a star's life.
And this is how we have snakes.
That's right. So what you end up with in the most massive stars is this. They actually separate, well, again, all this is theoretical, but the idea is that they, because of the weights, right? Now you're thinking atomic mass in terms of what these nuclei are made of. They're going to sort themselves by weight. So the hydrogen burning layer is just below the photosphere there. The outer layer of the sun, which is of the star, which you can actually see. Now below that is where the hydrogen is burning. Below that, you've got the helium layer, then you've got carbon layer, oxygen layer, neon layer, magnesium layer, and the silicon burning layer, and then in the center is the iron core, which won't burn.
So weird. The iron
Right.
won't burn.
Now this is showing you a really clean. It never looks like this, but this is the basic concept. All of this is moving
it's
around.
Be all convective.
Yeah,
and
it's
stirred up a little
convecting or
bit
whatever, and the
just
iron is being made all throughout this and slowly drifting down.
Right. Raining.
Yeah. And the idea, and this silica layer, the silicon burning, I was reading in many places, scientists were talking about once the really big stars, they get to the part where they're burning silicon, it takes less than a day for it to burn all that fuel from silica into iron. And then it starts to quote unquote run out of fuel and the temperature starts to drop, and the temperature, which was keeping the star expanded from collapsing, that balance fails, right?
Yeah, so pressure is increasing while temperature is dropping.
Yeah, exactly.
Which is...
So this is an example of, this is one artist's attempt to show relative star sizes. So our sun is up on the upper left there, 695,700 kilometers in radius. And then it shows Sirius, Pollux, Arcturus, and then this big giant one that covers the whole screen that is like 1 billion kilometers in radius. Right. And here's another one. This is a simpler one, but you can see our sun is that tiny little period in the little dot in the middle. Yeah. These are the big stars around it. So it's these giant ones, these big orange or yellow stars that are making all the really interesting higher elements, right? The smaller ones, they won't get that far. Some of these will get stuck at the carbon level and turn into white dwarfs or whatever. But this process that we've just gone through here, this is what generates all this, plus the explosions of these things, the resultant collapse of these things is what generates all of the elements that we know about. And they turn into things like this. I just love this picture. This is the supernova remnant. I don't know how to say it. Simius 147. About 40,000 years after the explosion is the light we're seeing right now.
God, that's awesome.
It is 140 light years across. So you could do some math there and figure out how fast that stuff's been moving. It's taken 40,000 years to go 140 light years. That's pretty quick.
Wow.
Yeah.
So quick thing to add. So at the point where you hit iron in the fusion cycle, it requires a greater amount of energy than it yields to move past iron. So that's your tipping point.
That's right. Iron is the ash of that kind of fire.
Right.
Yeah.
That's why it's star ash, because once it's not so much that it wouldn't burn if you had a way to do it to create a greater amount of energy within the system, you could.
It does when they explode.
Right.
It's just that iron will not create a self-sustaining chain reaction no matter how much energy you put into it.
Right.
Yeah. So yeah, that's a good point. And then we have a lot of people know about this is the Crab Nebula. This is another absolutely beautiful picture. This is a composite.
Now these are dark. I mean, they're in terms of visible light. So this is like radio telescopes.
This is everything.
Every spectrum that they can find, and then they're moving. They're shifting the frequencies into the visible spectrum so that they can show you the color.
And the colors that you're seeing in this particular image are showing you the elements in the material. I don't remember what the colors represent, but there's oxygen and nitrogen and all that.
Okay, so because what I would think is when they shift it to the visible spectrum, maybe what's actually there. Like we've talked about this before, that the visible spectrum is like less than an octave. In other words, like in wavelengths, that's not even double. Like you start out with one wavelength and then you double the length. Mm-hmm. We can't see; it's already out of our vision. Right.
Yeah.
If what you start with is at the edge of like the high frequency of our vision.
Yeah.
So this is probably many octaves.
Yes.
Right. And so they're having to change the ratios.
Yeah, this is ultraviolet, gamma, radio, visible, optical. I mean, it's every instrument they could point at it, they did, and then they used the Hubble to get the overall optical shape of it, and then they took all that other data and they colorized it to show you the elements, which is information they got from most of the other types of sensors. Yeah, and one thing that they pointed out when I was reading about this, again, this was a supernova explosion, is there's like an equatorial band going across the middle of it from upper left to lower right. And that is still unexplained in terms of physics. They don't understand why that happened. And then the weird, what they call the ghostly blue glow that's in the middle, that is radiation from the remnant pulsar that's in the middle there somewhere.
Oh.
Yeah. So in the middle there somewhere is a very, very hot neutron star that's spinning extremely fast and pulsing. That is all that's left of the star that exploded.
Yeah, it looks like there's like this circular thing going on right here.
Yeah.
That is super cool.
Yeah. So this happened. Ancient astronomers recorded the actual nova light reaching Earth in AD 1054. We've talked about this often on the podcast as well.
Yeah, at Chimney Rock,
Chaco and culture.
They had lined up. They'd made alignments to the Crab Nebula.
It was a guest star in the sky in 1054. Chinese astronomers recorded it. It was recorded in Korea, and in the Americas. It was noted all over the world. It was very bright.
Wow.
It is about 6,500 light years from us. It's now 11 light years across. And it is still expanding at 930 miles per second, or 0.5% of the speed of light. So you look at that explosion and you're like, wow, that's beautiful. But it's actually moving really fast.
It's still exploding.
It's just, it's so huge that we can't see it. But, it's only been expanding like that for 1,000 years, and it's 11 light years across. So
I wonder, man.
But I just love this picture. This is a very high resolution version of it.
It's 11 light years across. So if you went into like some of the thickest looking colored stuff,
you'd need to be moving at the same speed it was, or else it would tear you apart.
Well, yeah, like you're moving at the same speed it is, but it's like you probably wouldn't even know. It would just be dark.
Yeah, I don't know how much you would notice it. Yeah. It would probably still be very hot. So if you
very hot compared to the background temperature of the universe, or like.
Yeah, I don't know. I think it's probably still pretty hot. It might tear your ship apart. I don't know. This is a great question. Like, how thick is that stuff? Is that what you're asking?
Yeah, I'm imagining, because it's so huge that if you went in there, it'd be like, well, you'd be lucky if you ran into something.
Right. Yeah.
You know what I mean?
Yeah. And it's mostly gas.
Yeah. That's yeah.
Yeah.
Wow. Super cool.
So here's another interesting version of the periodic table. This is showing you how the standard model views the elements in terms of how they were generated by these various cosmological processes. So you see there. So up at the top, we've got the Big Bang fusion is blue, dying low mass stars, which is like our sun. It hasn't died yet, but it's a low mass star, is green. Exploding massive stars is yellow, right? Cosmic ray fission is like a pink color. Merging neutron stars is purple. And exploding white dwarfs, which is the standard candle we were talking about, is silver. So if you look at hydrogen, it's all blue, showing you that the standard model views all hydrogen was created in the Big Bang fusion process, which makes sense. Wow. right?
Yeah, because you had to have that to begin the star process.
Helium, on the other side, the next light element, most of it was created in the Big Bang, but some exploding massive stars and some dying low mass stars have made some.
Yeah.
You see that? Mm-hmm. So yeah, that's hydrogen, helium. And then if we look at like oxygen, all oxygen is made by exploding massive stars. Our sun, which would, when it's dying, it will be a dying low mass star, will not make any oxygen. It will make some carbon and nitrogen, but no oxygen. And if you look at iron, most of it's made by exploding white dwarfs, which was something that surprised me. But some of it is made by exploding massive stars, just under half. I like this. I think this is really interesting.
Yeah, that is cool.
And then if you look at these other interesting metals that we have, gold, iridium, platinum, silver, and mercury, most of these are either made by merging neutron stars or dying low mass stars.
Yeah, that's...
Iridium is almost all made by merging neutron stars. Think about that. Really interesting. Most gold is made like that too. All of these are...
Yeah, and remember the story I brought a couple weeks back about the gold? They're like, where did all this gold come from? How did all this gold get on Earth? Because if it's strictly from
merging
neutron stars, like according to our probability calculations, there's not enough of those in the universe to account for the amount of gold we find.
That's right. Why does the universe have so much blinge?
Jesus. That's right.
But it's interesting how all of these, gold, silver, mercury, they skip the exploding massive stars. Dying low mass stars will make them, but the big ones won't. I don't know. I find this whole, I spent a lot of time looking at this and it's like, wow, this is really interesting. Whether it's right or not, I don't know. Again, it's standard model. And then of course you have this string of stuff at the very bottom, which is gray, human synthesis, no stable isotopes. These are elements that have only been found artificially in the lab and none of them are stable. Mm-hmm. So as far as we know, the universe doesn't make that stuff, but it could. So it might. It's just not stable enough to stick around long enough for us to find it in a natural setting. Now we need to take a break.
Oh, yeah.
Yeah.
Shit. Forgot about those. This is awesome, man.
All right.
Thanks, buddy. Learning new stuff.
Learning new stuff.
We'll be right back.
We're back, ladies and gentlemen. Brothers of the Serpent podcast, second hour, sort of, technically.
According to the standard model.
Yes, the third segment is maybe what I should say. And we're going through this presentation that I built about stellar nucleosynthesis, and then we're going to be getting into various techniques for dating objects.
And we have...
Oh, yeah, we have some beers.
Cheers.
This is the
Birch beers.
Happy Camper IPA Birch beer.
This is the Desert Fog. We can trade off.
Yeah. Cheers.
Cheers, buddy.
All right.
COVID cannot live in good beer. Oh, man.
Hey, that's good.
That's delish. Thank you, buddy.
Yeah. Okay. So let's move on from this. This is I can talk about this for a long time. I just find it really fascinating how all these elements come about. But
that's a really cool thing you found there.
Yeah,
I have to say.
So next thing we're going to look at other massively energetic processes in the universe. This is an artist's depiction of a quasar. This is aside from the stellar processes and then the novas and supernova explosions, this is another thing that generates enough energy during its process that it makes a lot of the higher elements. Probably, right? This is a lot less well known than stellar processes in terms of how they've been able to study it, but quasars are the most energetic objects in the known universe. The name comes from quasi-stellar objects because when they were first pictured, they looked like really bright stars. So this is an actual picture of a quasar.
Now, is that the
Quasar 3C273 by the Hubble.
those beams coming out? Are they real, or is that sort of an artifact?
No,
of
that's
the
an
lens?
artifact of the lens.
Okay.
And you can see that around it are galaxies. So this gives you the scale of this object.
Oh wow.
Okay. This is approximately 2.5 billion light years away, which is lucky for us. We don't want any quasars closer than that.
Is this like one of the closest ones?
Yes. So I think this is the closest one known. But yeah, when I was looking at this image, I was like, wow, those are galaxies. So that shows you. And this thing is as far away as those galaxies are.
So the fact that they're that far away, I mean, that's telling you their age.
Yeah.
In terms of like when they formed at like through the process of the universe.
It's telling you. Well, yeah, and it's telling you how long ago that this quasar was taking place.
Yeah, because the lights are.
We don't know what it looks like now. Yeah.
Right.
Yeah, but
but because it's the
it
closest.
was doing that 2.5 billion light years ago, or years ago. And that other thing, the orange thing in the lower right, that's a star that's nearby. That's a relatively close star.
To us.
Yes, to us. But you can see what's the backdrop of that image is distant galaxies. Those are all galaxies all around that
Right.
thing. So that's the scope of this thing. It's as far away as those galaxies, and yet it looks like that.
That's insane.
Yeah. So this is a picture of an active galactic nuclei. Now, these are similar to quasars, they think, in terms of what's happening. They're just not nearly as energetic. Basically, you have these galaxies have massive black holes at the center. They call them supermassive black holes. And it's absorbing a ton of material for whatever reason. Its accretion disk is actually, a whole bunch of it is falling in. And so the spin of the accretion disk is generating all this pressure and temperature close to the edge of the black hole. It's tearing matter apart. It's causing the same thing that's happening in stars, but it's much more energetic. And because it's spinning, it throws these huge plumes out in the north and south poles. And this is all thought to be a magnetic stuff, but you can see these jets coming out, and then there are like these explosive clouds above and below the north and south poles of this galaxy. So this is like a quasar that's not nearly as powerful. So what's all around that are nearby stars to us. But this thing is Centaurus A, and it is about 12 million light years away. So it's a nearby galaxy, basically. And we're kind of looking at the galaxy edge on. You can see the material there. And it's interesting because some of the way the dust is when I was reading about this, some of the way the dust that you can see, that dark material that's distributed around the galaxy, it looks like it's being shredded by this giant, massive process that's taking place in the center of it. So we're also lucky that our galaxy doesn't seem to be doing this. We don't have one of these in the Milky Way, thank God, because that would also be killing us. So you don't want a quasar very close, no closer than a billion light years or whatever. You don't want one of these in your galaxy. And if it's happening to a galaxy nearby, you're lucky that
the poles are facing away.
Or
not. They're
not facing us. Yeah.
Yeah. They're perpendicular to the plane of the. Well, I don't know. Whatever. They're pointing elsewhere.
Yeah. That's right. So, no matter what energetic process we're looking at, they make things we call cosmic rays. So this is another artist's depiction. So you have some enormously massive cosmologically energetic process, whether that's a hypernova or a supernova or an active galactic nuclei or a quasar, whatever that is up there. It is generating when this process takes place, you've got all that same fusion we were looking at in the nucleosynthesis part. So you have a plasma state where electrons are stripped away from the nuclei. And now since we're doing billiard balls here, let's go to billiards, okay? Because this is everybody's done this. You go to break the damn it, now I just lost the term. You're going to break the, what is it?
I don't know.
You don't know either. you're going to break, right?
Yeah, you're going to break.
You're going to break.
You're breaking.
Yeah, so you've got the triangle of balls there, and whoever set it up didn't quite do it right. So you nail that cue ball, and we've all seen this. It flies over there and it hits that triangle of balls, and like 2 of them go flying off like crazy, and the rest of them sort of sit there, and they might spread out a little bit.
Yeah. And then you get ridiculed.
Yeah.
Yeah.
Those 2 billiard balls that went flying off are the cosmic rays in these things. Okay. The rest of them spread out a little bit. So like those supernova explosions we saw, like the Crab Nebula and stuff, you've got all this material that's sort of spreading out, and it's moving fast and it's very hot, but it's not relativistic, really. I mean, yeah, 0.5 of light speed is pretty fast. But some of these particles get kicked out at 99.9999% of light speed. And remember that these are massive particles. So most of them are alpha particles. So they're the nucleus of helium, stripped of electrons. So it's 2 protons and 2 neutrons. And in the process of the explosion, or whatever the energetic thing that's taking place way out in space is, that particular particle is in the right place to get all of the energy directed at it from a whole bunch of vectors, and it gets kicked out from that explosion way faster than everything else that's involved in that explosion.
So does it have a lot more gravity?
Yeah,
Because
presumably.
it's traveling so fast.
Yes.
It's way more massive
Yeah,
because of that speed.
absolutely.
Therefore, it's
Yes.
got a lot more gravity.
Yeah, and we'll get to that.
So maybe I'm just going back to, I can't remember his name. That, if there's all these cosmic rays flying around everywhere, there's shit tons of mass everywhere,
Yeah,
but not a whole lot of matter involved.
right. And if they're accelerating, they should be gaining mass. Yeah. Is that what you're getting at?
Yeah, the point is that they wouldn't, in other words, because they're so massive because of their speed, their relativistic speed, there should be a lot of gravity. If you take these
relative to those particles, there's a lot of gravity around them. Yeah.
So you're looking out at a giant cluster of galaxies, and there's
cosmic rays flying
cosmic rays everywhere.
Yeah, that's a good
And
point.
so there's not a lot of actual stuff for light to be interacting with. So there's, like, in other words,
they would have gravitic
matter,
effects. Yeah.
the chunks of shit that can interact with light. There's a few of those, but because they're relativistic, there's a lot of gravity involved because there's a lot of mass.
Yes.
That's what his point was.
So maybe cosmic rays could be part of the missing mass,
the
missing gravity. Yeah, that's a great point. So go ahead, Watcher.
I was actually just having the same thought that, like, maybe we don't need dark matter because you have these massive particles. But were you looking for the term rack with billiard balls?
Yeah, rack. Yeah, well, no, when you just like, are you going to break or am I going to break? Is what it's called. But I was
Right.
thinking there was another word
for the cluster of balls there.
yeah, when you're going to break those things, the triangle of balls.
Yeah, the triangle of balls is the rack. Break it, and they go off everywhere. All right, fair enough. By the way, it is way easier in the chat window when I don't have to try to time the good pauses in conversation.
Yeah.
Because I've been holding on to that one for at least 2 minutes.
Oh, well, sorry about that. Yeah.
No, you're on a roll. It's good stuff.
Okay, so here's another artist's depiction of what cosmic rays look like when they enter Earth's atmosphere. Okay. So I got a couple of things here. The most energetic cosmic rays are also known as ultra high energy cosmic rays. They're 40 million times the energy of particles in the Large Hadron Collider.
Jeez.
So this is why I'm talking about the really high energy ones that come burning in. They are extremely massive because, first of all, when I say massive particles, what I mean by that in terms of physics is they're not electrons or protons or photons. They have mass, right?
Right. Yeah.
But then when you say they're
It's not massive in terms of size.
no,
It's massive in terms of energy.
yeah, and mass, right, which is basically
same
the
thing,
energy,
yeah.
yeah. But then when you're talking about relativistically massive, their very velocity, their speed, which is another energy amount, is also adding mass, right? I know. So some of these UHECRs, the ultra high energy cosmic rays, have the same kinetic energy to a 90 kilometer per hour or 56 mile per hour baseball. Now think about that. 2 protons and 2 neutrons stuck together that have the same kinetic energy as a baseball thrown at 56 miles per hour. So you got this, sub-microscopic object that nevertheless has the same, it should have the same mass because its kinetic energy is comparable. So yes, it's a baseball of gravity out there. So yeah, they're flying all around. You're right. You got all these baseballs out there. They're totally invisible until they run into something.
Right.
And yet they have the same gravity, quote unquote, as a baseball. So yeah, if you got a lot of those, that's a lot of baseballs. Baseballs can add up, right?
So after they go through all this atmospheric interaction, that's going to be taking a lot of that away. I mean, imagine like you throw a baseball at 56 miles per hour. It's not going to. No, it's going to be
doesn't make it
so weak by the time it's
right. So you have to vision.
It's going to burn up in the atmosphere. Basically.
Well, what you have to envision here is.
But that's because of its size.
Again, with the billiard ball thing. But think of
this is kind of a terrible. This thing is not one. It's so small that it's not really running into anything hardly.
Well, it's definitely running into stuff. It does.
But I mean, because it's so small, it's not like a baseball in that sense. Whereas a baseball is hitting trillions of molecules of air.
Right.
At a time.
No. But all this has to do is start hitting one, and then it causes this ridiculous.
Okay. Then it causes the chain reaction.
Yeah. So. Think of like you're out on the Autobahn or whatever, and you're in this car and you're going, 250 miles an hour or whatever. You got this badass car and you've got it maxed out, and then you come into a city and you don't slow down, and there's traffic. What happens? Eventually, you run into the first car.
Right.
That car runs into 3 other cars. Those cars run into a whole bunch of other cars and go through some windows and smash them. That's what happens here. So here's another depiction. So you got a supernova up there on the upper right. And then you've got some cosmic rays coming in. They make their first interaction way up there in the upper atmosphere, and then you have all of these reactions afterwards as that energy is dispersed.
In the upper left.
I'm sorry, in the upper left.
Okay. I was like,
yeah, sorry.
No, it's cool.
Upper left. Yeah, so that's the supernova, and cosmic rays are coming in as a result of it, and.
They're hitting all this stuff.
Way
up
in the upper atmosphere. They run into one, and then that runs into a bunch, and it makes it all the way to the ground. But by the time it gets to the ground, it's not nearly as energetic as it was up there. But the whole time it's doing this, it's doing stellar nucleosynthesis on an atomic scale. Okay, it's changing elements into other elements and knocking neutrons and protons out of things and
doing that same exact stuff.
Yes.
Yeah. But it's okay. So.
I can't see the.
Take all of this. What are you trying to see?
I can't see the text when that thing is right there.
What text?
The text that appears when I do that.
Well, I want to say, so you take all of this area, right? Mm-hmm. You put it under the same pressure that's in the hydrogen fusion layer of the sun, and it's going to become very small.
Oh yeah.
And
the
then,
sun's getting hit by the
So this is my point: is that you compress all of this, you put the same pressure that's on the sun with this entire volume of air in the atmosphere.
Yeah,
and that chain reaction isn't going to slow down, but going to speed up.
Yeah, that's right. Absolutely.
Whereas in this scenario, it's so cold, it's so expanded, the pressure is so low that everything is so far apart, there's not enough to run into to create the chain reaction.
Yeah, it won't start up nuclear fusion.
It's not creating a chain reaction that has a positive curve or whatever.
Right, yeah, that's right.
Okay.
So, again, what we're looking at, this is really, I find this picture interesting, but it's a complex, somebody has tried to depict what this chain reaction looks like, and it's, it's a train wreck, basically.
Yeah.
Everything running into everything else as a result of this one tiny relativistic massive particle hitting one thing in the Earth's atmosphere, and then probably a whole bunch of other things after that. But everything that it hits a whole bunch of other things, and those things all hit other things. Okay. So yeah, infalling cosmic rays cause enormous high energy collision chains in the Earth's atmosphere. And they can generate isotopes of existing elements in the atmosphere. So again, let's look at what's in the atmosphere. We got nitrogen. It's 78% of the Earth's atmosphere. And you'll notice 7 protons. Nitrogen is, the most common isotope of nitrogen is 14. 7 protons, 7 neutrons, and 7 electrons, right? That's really close to carbon, which is 6, 6, and 6, carbon 12.
Oh, man. Mark of the beast right there.
That's right.
The old
Now, there's hardly
666.
there's hardly any carbon in the atmosphere. But nitrogen, there's tons of it, 78%. So what is that, when that infalling massive relativistic particle comes burning into the Earth's atmosphere, what's it most likely to hit? It's got a 78% chance of running into nitrogen. But it's going to just completely destroy that nitrogen. A whole bunch of stuff has to happen first, and this is the process. We're not going to go into all that first stuff. We're just going to look at the end of the process. So way down the collision chain, you end up with fast neutrons from cosmic ray collisions, okay? This is the fast neutron. So the cosmic ray proton comes in, it runs into a whole bunch of stuff, it causes a whole bunch of things to happen. The energy levels have to keep dropping as these collisions keep taking place. Right. Eventually, in this process somewhere, and actually probably in a lot of places within the process, you end up with what's called a fast neutron. It's been kicked out of some other nucleus by these collisions. And now it's moving quick. It's got a lot of energy related to it. It's not relativistic, but it's moving fast. Okay. So that runs into a nitrogen-14. This neutron embeds itself into that nitrogen-14 nucleus and kicks a proton out of there. That's this second process. Okay. The loss of that proton results in the loss of an electron pretty quickly, right? The other electron leaves or something. I couldn't really find good details on this.
So the proton becomes hydrogen.
Yeah, probably.
It's
It's also going to be fast, so it's going to do some other stuff.
okay.
It's going to be part of the collision, but yeah, it'll eventually probably turn into hydrogen and
bond with oxygen.
Yeah. So the result is carbon-14. So now you notice that carbon has this. So nitrogen-14, the stable isotope of nitrogen is 14. Now you've got carbon-14. It has 6 protons, 6 electrons, and 8 neutrons. Because you started out with 7 protons, 7 electrons, and 7 neutrons, but a neutron comes in, adds itself. So now you've got 8. 1 proton leaves, so now you got 6 protons. 1 electron leaves, so now you got 6, 6, and 8. This is an unstable version of carbon.
And that comes from the nitrogen-14?
Yeah.
Wow. Okay.
The fast neutron has to run into a nitrogen atom to do this.
To make carbon-14.
That's right.
Wow.
So you can see how this is interesting because it's the carbon-14 exists because we have a whole bunch of nitrogen. Otherwise, this process wouldn't take place.
That's really weird.
So when we get into the carbon dating, one of the questions is
How often
has
does this
Earth's atmosphere always had this much nitrogen in it? You have to ask these questions.
That's a good question.
Right?
Yeah. Because we've always talked about...
we know how many cosmic rays are there, but how much nitrogen has there always been?
Yeah.
Surely it's fluctuated. Now, has it fluctuated in the past 60,000 years? Well,
Which is the kind of the day range for...
yeah, that's the maximum-ish. So down at the bottom here, I'm showing carbon-12, which is the stable version, the most common version of carbon, 6 protons, 6 neutrons, and you can see that. Carbon-14, you can see it's got an extra couple of neutrons in there, and this is an unstable nucleus. It isn't even. It vibrates badly or something, and eventually it wants to get rid of those neutrons.
It's all rickety.
Yeah. It wants to get rid of those neutrons.
A couple of hubcaps fly off.
That's right. But it has the same number of electrons, so it is chemically exactly the same as carbon-12.
Right. Yeah.
So the final step here...
Which doesn't tell you much. I mean, chemists, come on.
Yeah. They don't really know anything. We already know
I'm
this.
just kidding.
So the final step here, unstable radioactive isotope, which is carbon-14, it bonds with oxygen to become carbon dioxide and enters the biosphere because it's chemically exactly the same as C12.
And becomes part of this carbon cycle.
That's right.
That's cool. I just wanted to say that it took physicists like 50 years to show the chemists that they were right about what they were doing.
Look, guys, we've done all this work. And we've proved that this whole time you've been right. Okay.
Even though you didn't know what you were doing.
That's right. So back to this picture. Now we're going to look at... So that C14 is called a cosmogenic nuclide. Okay? it is generated cosmogenically. So here's some examples of these. Carbon-14, which we've been talking about, we will keep talking about. And the half-life. So the half-life of C14 is roughly 5,730 years. And then calcium-41 is another one. Now, carbon-14 is by far the most often made by cosmic rays. Most of the other ones, they don't get made nearly as much because, again, carbon-14 is sourced from nitrogen, which is very, very, very abundant.
Yeah.
So you have calcium-41, its half-life is about 100,000 years. Chlorine-36, its half-life is about 301,000 years. Aluminum-26, its half-life is about 730,000 years. Beryllium-10 with a half-life of 1.5 million years. And iodine-129, 16 million years half-life. All of these are cosmogenically generated by cosmic rays. Beryllium-10 has been... And they're starting to use, well, they try to use all of these in dating, but the amounts are so tiny that it's hard. You got to have really sensitive instruments, and it's got to be the right materials and so on and so forth.
Harder to find a pure sample too, because like one of the things with carbon-14 is you want to make sure your sample isn't contaminated, right? So
Buy stuff that's not dead.
If there's a lot of it, it's easier to find an uncontaminated sample.
Yeah. Yeah.
You can remove parts of the sample that may have been contaminated and still find some carbon-14. Whereas if you have something that's not very abundant, you may not have the luxury to just like remove possibly contaminated materials and still find that.
Yeah, that's right.
Yeah.
I also want to point out before we leave this picture that those
Go ahead, Watcher.
Those lights on the grounds are not explosions from the cosmic ray.
Okay.
I think those are supposed to be cities.
Also, one of the difficulties you run into with the non-carbon compounds is in organic tissue and the process where the carbon is assimilated by plants and become, present in whatever they use as a material to write on or whatever it is that's going to be in, again, organic tissues. It's not going to be abundant at all. Like you do have iodine and aluminum in, for example, the human body. But compared to the amount of carbon present in the human body, it's not even remotely close.
Absolutely.
You're talking
Absolutely
powers of 10, 10 to the 5, 10 to the 6.
Yeah.
more
And these other
abundant.
ones, calcium, chlorine, aluminum, beryllium, and iodine, none of those are used to measure organic stuff.
Right.
The carbon is used to measure to date organic stuff. I mean, they might try to use, I don't know, but as far as I know, like for beryllium, that these are used in dating. They try to use these to date other materials besides organic things, as far as I know.
One last thing while I have your attention. In case you were curious, an electron would have to move 3.32 nonillion or 10 times 10 to the 30th power faster than a baseball to have the same mass.
Wow. What about a couple of protons and a couple of neutrons? Because that's usually what we're talking about here. A helium. It's an alpha particle, a helium, a nucleus.
Gotcha.
Yeah. So work that out.
1 moment, please.
We'll keep moving on here.
Yeah, check the chat window in a moment. I'll have it.
Okay. Thanks, Watcher. Okay. Carbon-14 dating. So the old method they used was called beta counting, which basically means that they counted the beta particles. These are the radioactive particles emitted. There was where 1 or 2 neutrons is leaving. It's not an alpha particle.
Yeah,
it's a less deadly, less version. I couldn't exactly figure out what they're talking about, but it's not a neutron. It's other pieces, right? But yeah, beta particles emitted by decay during testing. So you'd get something and you'd bring it in there and you run your Geiger counter next to it, a very sensitive one, and you wait and count and try to figure out how much C14 is in there based on what's decaying now. That's the old method, when they were first doing it. Current method uses accelerator mass spectrometry. It directly counts the number of C12, which is regular carbon, and C14, which is the radioactive isotope of it. This gives you a more accurate count, and you can use much, much smaller samples. And you're directly counting beta particles being emitted by decay during testing. You need a big sample so that stuff will decay.
Right.
And this is a picture of one of the labs that does this.
Does which one?
The accelerator mass spectrometry.
yeah.
So that whole the sample goes in over there, and I couldn't figure out exactly how this works. I saw some ridiculously tiny diagrams, but there's a whole process here in which they break it apart, they turn it into a gas, and then they run it through an accelerator, and then they count the C14 and the C12 by spectrum on the other end.
Right.
So calibration. Now this is interesting to me. Calibration.
So they're basically in that process. They're breaking it apart.
Yes, you have to destroy.
They're shattering it and then counting the counting up the pieces or whatever that they get on the detector.
Right. That's right.
Yeah.
So the calibration relies on the use of objects that have known ages outside of the use of radiometric measurements. So in this case, usually dendrochronology and dendrochronology is the best calibration for C14. They've also used lake varves in some cases and ice cores.
Ice cores, yeah.
And this is a picture of a
counting rings.
Yeah, this is a picture of a bristlecone pine stump, which is the most common in the northern hemisphere because these trees live like 4,900 years. Or they're the oldest known one is really, really old like that.
I wonder. I don't want to take this off on a tangent.
What? Tangents are what we're about. What?
All right. Well,
we're going to go into dendrochronology later, so if you got questions on that, we can do.
Well, yeah, it is a dendrochronology related thing.
So we'll do that when we get there. So this is the IntCal 20 calibration curve that I found. It's cool because this shows you how this works. Basically, if I get a radiocarbon date of 20,000 years, for example, I look over to the calibrated line, and that tells me that it's actually calendar age around 24,000 years old.
And this is
the latest calibration curve for the northern hemisphere.
And this is using all of those things?
Stuff, yeah.
Dendrochronology, ice cores, all that stuff?
Yeah, dendrochronology all the way up until about 12,000 BP. Or I'm sorry, BC probably. Maybe it's BP. I've got.
Oh, okay. And then other ice cores and other stuff before that.
Yeah,
before that.
They've got calibration data all the way out to the limits of C14 dating. It's not nearly as accurate. You can see how down here they've got a lot more points in the graph. You can see how the line is much more detailed, and as you get out, it's much less detailed. That's because they've got fewer and fewer calibrations, okay? But down here, from 0 to 10,000, there's a lot of calibrations. That's why the line is so detailed down there.
Yeah.
Now,
cool.
so if you zoomed in, you would see a lot of detail.
All these little fluctuations.
But out here, you can tell there's fewer and fewer points as we get farther and farther away from the present. But I just wanted to show how it works. You know, you've got the one-to-one line going down the middle, which is what you would hope it was. It isn't, though. You get a 20,000-year radiocarbon date. It's actually going to be calibrated around 24,000 years.
Cool.
So, carbon-14, the method is counting the C12 and the C14 in the sample. The limit of this range of this dating is about 60,000 years due to the short half-life of carbon-14, which is 5,000 years.
Once you get past that, it's...
Eventually, you run out of C14 and you can't count anything. Yeah. Calibration with dendrochronology provides more accurate dates for the past roughly 12,000 years.
So, well, just going back to the C14, you find an organic sample, and then you take it for C14 dating, and you don't find any. Then you know it's older than 60,000 years, right? I mean, that's kind of the idea.
Yeah. Yeah.
It hasn't been in the life cycle, in the carbon cycle for long enough for all of that to decay. So you don't know how old it is, but you know it can't be
younger than 50 to 60,000 years. Yeah.
Still helpful.
Yeah. So assumptions and problems with this method.
And
it can only be used on organic material. It will not date lithic artifacts. So it can't be used to date stone, all that kind of stuff. And the contamination of samples by living organic material can skew the date. And even if that living organic material was living 10,000 years ago, it can skew the date.
If some worm got in there and there's some
and took some craps
detritus or whatever.
Yeah, exactly.
Yeah, and that gets into your sample, and it's yeah. That must be really hard to.
So the hope is that those types of contaminations, like microbiological contamination, like for example, if you have wood that was buried in an anaerobic situation and it was buried like that for a long time, and then some other geological processes bring it up to the surface, and then it gets buried again, and then you 5,000 years later pull it out to date it, you may get the dating of the last time it was exposed to the biosphere as opposed to the age of the...
Which is why it's strange that the wood fragment from the
King's
the
chamber,
hook handle rod
hook handle rod
was 500 years older.
Yeah, that's right.
If it was
Very old tree.
contaminated, it
Very
would have
old
been
tree.
younger.
Right, that's right.
So that's interesting. It still could have been contaminated, which made it younger than it really is.
It most certainly probably was contaminated. It was sitting in a cigar tin for one thing.
But I mean,
It was handled by people who had no idea of C14.
That's what I'm
dating.
saying. So,
yeah,
so the contamination will only make it appear younger.
that's right. Always.
So the fact that it's only 500 years older,
probably means that it's older.
it's
than that.
even older.
Yeah. Okay. All right.
Cool.
Taking a break.
Yep. And we are back, ladies and gentlemen. I think possibly the final segment.
Maybe.
Maybe. We'll see how far we get here.
We have some Discord questions too to do at the end, so
Oh, okay.
yeah, might be a long show. No problem.
Yeah. I'm good to go long. Got good beers
Good beers
and
good smokes.
fine tobacco.
Yeah.
This Mark Twain is quite nice. Mild and tasty.
Yeah, the
Thank you,
beer's
buddy.
really good, and I'm having to resist drinking it too much because it'll make me burp during the show. Can't have that.
That's what the mute button is for.
So the final point here on the assumptions and problems with carbon-14 dating, and this is what I was originally getting to in episode 3, is that it relies on the assumption of a constant rate of cosmic ray bombardment generating relatively constant amounts of C14 in the atmosphere. And what I would add to that now is
Constant concentration.
constant concentrations of nitrogen, which is
Great
what results
point,
in C14. Okay. Dendrochronology. This counts tree ring growth layers. Each ring represents a year. Some of this is pretty simple. It's a very accurate method. Layers can be matched to other samples to generate a continuous timeline. This is part of what makes it very useful. You can, because trees in similar areas or even in sort of widely dispersed areas react similarly to climate changes that are global in scope. You can match layer growths to other trees that aren't as old or whatever and kind of make a continuous timeline. Then the identified layers can then be carbon dated to provide the calibration, which is how that is done. So as of 2020, securely dated tree ring data for Northern Hemisphere goes back 12,310 years.
There seems to be a veil there.
Yeah. Somehow all the trees disappeared under that. Assumptions and problems
really
with this.
messy.
Yeah. There's not really many, but the precise date of the death of the actual tree requires a full sample all the way to the edge, which is not always especially when you're using, for example, timber in some ancient site. You might be able to match some parts of that, but you can't actually tell the age of the tree, the date of the tree, unless you've got, and most timber doesn't go all the way to the edge, right? Because you cut the edges off.
Yes.
And then, of course, it's limited in the scope of time. 12,000 years. I mean, they're still working on it. They may add more, but you go much farther back than that and you start getting petrified wood and stuff. So, and then, of course, petrified samples do not apply.
Dang it.
So I was just looking at this, imagining, counting the rings and, 1, 2, 3, 4, 5, 6, 7, 8. Damn it. 1, 2, 3, 4, 5, 6. Oh, shit. 1, 2, 3, 4. Especially when you get to the outer ring, you can see there it had some problems in the outer layers, and they were much smaller, right? The tree was growing vigorously for a while, and then it slowed way down. And there might be a climate problem there. It might be something else. And you can see that this is the other interesting thing about it is only the wood at the very edge of the tree is alive. So the wood in the middle, these other layers, they're basically dead wood. They provide structure, but they're no longer in the carbon cycle. So this is why you can carbon date them.
Well, they uptake water.
All that happens
Right.
on the outside for the most part. Yeah, I'm pretty sure.
Okay.
So here's an example of one with dates marked. The tree started as a little sapling in 1623, and then they've got 1634, 1697, all the way up to 1996 when it either was felled or fell over or it died. But those are the date marks, and you can see there's just interesting patterns in there. And here's another one. It was born 1527, and then there was a mega drought there somewhere in the 16th century where it barely grew at all. The layers are very tiny.
It's really cool.
Yeah. Okay.
So before we go into that, I was just thinking, there's this book, and there is also an audiobook, which is what I got, but it's called The Secret Life of Trees. I highly recommend this book. The guy who wrote it he's a forestry guy. It's been a while since I listened to the book, but he would go into these forests and he was studying all these trees and their life cycles and all this stuff. And I think this had to do with logging and whatever industry, I don't know. But the point is, in the book, he just describes this scenario that is actually mind-blowing as to the way these trees interact with each other. And say you have this tree, it grows up from a sapling, and while it's a sapling in the forest, it's being sheltered by the other trees that are large, right? It's not getting very much sun, and it causes this real slow growth, which is actually helpful because if it grows too rapidly when it's young, it becomes susceptible to a lot of things. Freezing is one. Anyway, so this natural shading that the mother trees cause kind of helps the saplings get stronger and stronger, and eventually they beat out each other because the mother tree is dropping all the seeds all the time. And a bunch of them will take root, but only a few will be successful. And they struggle and they struggle, and they finally start reaching areas where they can get out and branch out and get into the sun and start gaining momentum. Inevitably, something comes along that may damage the mother tree. Some storm or whatever breaks some serious branches or something like that, and that provides this big burst of sunlight for the stronger sapling. And it takes over the other saplings. And anyway, this process goes on. What's interesting is that if the mother tree is felled or killed or in some way, the stump from a felled tree will still be alive and actually provide nutrients to the saplings long after the tree is gone. The stump is actually still actively engaging in nurturing the saplings.
Wow.
And I can't remember the exact mechanism, but one of the things that's really interesting, this sort of symbiotic relationship between the trees and the fungus or the fungi that live in the ground. There are types of fungus that sort of merge with the very fine ends of the roots of the tree. And they have this almost like a neural network. The mycelium is like going all through the ground and then merging into the ends of these roots of the other trees in the forest and creating this vast, gigantic neural network through the ground in the entire forest, connecting all these trees together and all these other plants, so that if there is a drought, for example, the mother tree can actually provide certain nutrients through the roots into the soil to the saplings. And also, if one of the examples he gave was if like some giraffes move in on way like, miles away, for example, into a forest and start eating all these branches off the trees, those trees start producing tannins, right? That go down into the leaves and everything and make them real bitter. and the giraffes will move on.
Yeah.
But they move on past the entire forest because the initiation of the production of those tannins that moves out through the trees is also causing something to change in the root system, which the mycelium carries that information to the other roots of the other trees, and they start producing the tannins. So the entire forest starts producing the tannins because of the new predator that's come in to start eating the trees.
Wow.
So I was just in this, for some reason, it was making me think about this dendrochronology. And it's like, man, it would be really cool if we could tap into those types of cycles, into the fungus that is connected to the trees, and the types of information that might carry on a microscopic level.
Yeah.
In terms of the history of the entire forest, because some of these trees that are stumps that have been around for 100 years are still active and doing certain things. They're not completely dead.
Wow. Yeah, and I wonder if there would be like heightened tannin levels in some of the layers that would tell you that during that period there was
exactly certain predators
and moved in and started eating the trees.
Yeah. But anyway, fantastic book, The Secret Life of Trees. Highly recommended.
Put it on the list.
Put it on the list. It's a good one.
Okay. Luminescence. Now this one, I was originally looking at thermoluminescence, and then I realized that that optically stimulated luminescence and thermoluminescence are based on the same principles. They just use different methods. So we're just going to talk about the idea of luminescence and how it works. Sort of how it works. A basic understanding. Because I don't really understand how it works because we're going back to nuclear physics. But absorbed radiation from the environment or cosmic rays will cause certain chain reactions in the materials in types of stone that will release electrons, cause electrons to be shed. And those electrons will be trapped in the crystalline structure of the material. Now we're talking about stone here.
After they're shed, they get trapped somewhere
Yeah, they
else?
get stuck.
Okay.
Yeah, in the crystalline, because they can't pass through. They don't have enough, they could pass through, but they're not quite high enough energy. This is why this is so useful, because luminescence is good for dating low thermal events, like being heated by the sun. You can date the last time it was exposed to sunlight using this method.
Okay.
Or the last time a fire was burned near it. Or the last time there was some geological event that raised the temperature to 500 degrees or something like that. Okay. So all of this radioactive activity within the stone or around the stone, whatever the sample is, whether it's a whole sediment layer or whether it's a little piece of stone that's trapped beneath a giant megalithic block, and you're trying to date, how old this block is.
The last time that piece of stone saw sunlight.
So saw sunlight. The radiation in the environment causes electrons to be trapped within the crystalline structures that are inherent in the stone. Okay. So then exciting the sample gives those electrons enough energy to escape.
Yeah. Gotcha.
Now you can excite this sample using either thermo with heat or optically stimulated luminescence using light. Okay, so what the difference in what they do, whether it's thermoluminescence or optically stimulated or some of the other processes, has to do with what the sample's made of. Because in some cases it's best to just heat it up a little bit to let those electrons escape.
And see what comes out.
Yeah. In other cases, the best way to do it is to hit it with a certain kind of light, green light or blue light, a laser or whatever. And you have to do this in a protected place because you need to be able to measure the very, very weak light that these escaping electrons emit, because as they finally able to escape, they emit a photon or whatever, the billiard balls again. We're going back to the billiard balls, except that this time the billiard ball releases a wave that also kind of looks like a billiard ball. It rolls past like a billiard ball that's waving or something.
Right,
whatever the photon is doing.
Got it,
yeah. So you need to get your sample, and it needs to be protected from being hit by the sunlight, because even a couple of minutes of exposure to sunlight will zero it out, quote unquote zero. It zeroes it. Okay, so you need to get it in the dark, keep it in the dark, take it to the lab in the dark, and then do either the thermoluminescence or the optically stimulated luminescence in the dark with very sensitive sensors. And when you do it very precisely, and you measure this tiny amount of light that these electrons emit. So the more light you see, the more escaping electrons there are, the longer this thing has been sitting in the dark. Okay, So yes, the dates are to the last time the sample was heated by sun, by fire, etc. And they call this a low energy measurement because all it takes is being exposed to the sun for it to be zeroed out. That's a low energy event. The range for thermoluminescence is from decades up to about 100,000 years, but there have been recent reports with much more sensitive instruments where people are sometimes getting dates of 200,000 or 300,000 years. So it's still kind of young, and it's getting more and more precise. Or I should say, it says more precise. And the margin of error is roughly 5 to 10% of the age that you get. So again, so let's go through this. When I was going through these and I'm trying to find, I want to know what the range is for this particular technique and what are the margin of error. I couldn't always find these numbers. And sometimes they were wrapped up in I'd read whole papers on people arguing with each other about what the margin of error should be on some particular technique. And it's all nuclear physics because they're looking at some kind of radiometric thing and they're talking about types of decay and how they should count them and what, and well, this kind of detector does that or whatever. And you can't find a margin of error because every one of them is different. But in some cases I was able to find them. And for luminescence, the margin of error is roughly 5 to 10% of the age of the object. So if you get something that's dated to 100,000 years by a thermoluminescence, your margin of error is 5% of that.
Okay.
Between 5 and 10%. Right. So between 5 and 10,000 years, plus or minus.
Yeah, well, so the younger it is, the more the smaller your margin of error. That's cool.
So the assumptions and problems with this, the amount of the radiation received by the sample must be estimated, including cosmic rays. So again, we're back to the cosmic ray problem. Have they been constant? No. We already know this because of calibration. And the other problem is back to that megalith. I go out there in the middle of the night when there's no moon and it's cloud covered and it's pitch black, and I'm very careful to tilt that monolith, and I get that little rock out from underneath there. Well, while I'm doing that, I need to get a very precise test of that area where that rock was sitting to find out what is the local radiation level.
Yeah.
Because I have to include that because that's how I count the electrons. Mm-hmm. If I don't know what the local radiation level is, and then I have to add in cosmic rays, and there are also cosmogenic nuclides and stuff like that, because not only can the sample be hit by cosmic rays, but it can be affected by cosmogenic nuclides that have been generated by cosmic rays since it's been in the dark. Right? So there's some error problems here.
Yeah.
But this is the big one. You've got to very precisely take the sample. And in some cases, what they'll do, if they're getting a big block of stone, like from some ancient building, you can, instead of having to flip the whole thing over, you can kind of dig down into the stone, but that damages the rock, right? So that so what they prefer to do usually, testing, you want to kind of get under there and scrape out some piece of it. So stratigraphic dating, this is a kind of relative dating. This is very simple. The deeper layers are probably older. This is the first kind of geological dating there was, right? Basically, you look at this strata, and you're like, the ones that are lower down are probably older than the ones that are above them, probably.
Yeah,
it doesn't
except
work
when they're flipped over,
Yeah, it doesn't work in all cases, but in general, it's true, and it's only relative. It doesn't tell you the age of things, except that you know that this one's older or that one's younger because they're on top or below each other.
Right.
So there's a whole bunch of this kind of thing that's called relative dating, and they're not very useful. And they're used a lot more in archaeology because they'll be digging down and they'll go through cultural layers, and they use a relative dating in the sense that, like, well, that culture must be older than this one. These people who are making these artifacts down here were probably here before these people making these artifacts up here.
Right.
So it just gives you a kind of a ballpark, but it doesn't actually give you any numbers. Unless you have numbers on one particular layer, and then you can start estimating, but again, it's not very accurate. But the reason I'm showing this picture is because this is an example of stratigraphic where you're like, yeah, those down there are lower or older than
and of course, the stratigraphic type will have proxies of other things.
Yeah.
Like black mats that point to an event that you can go look at places where that event may have taken place and then find other evidence of age.
Yes.
Yeah.
So that will be an example of this. Tephrochronology is an interesting one. This uses layers of tephra, which is volcanic ash from a single eruption.
Yeah.
Individual volcanic events produce ash with a unique chemical fingerprint that can be identified over wide areas, anywhere the eruption affected stuff. And if it was carried by winds and dropped down somewhere, you can often find volcanic ash from single eruptions over very large areas. Once that layer has been dated, it can act as a chronological marker at any site because they are uniquely chemical or chemically unique. They act like a fingerprint. So the problems with this one, it relies on the accuracy of other dating techniques because you have to date the tephra using something. This is an example of a volcanic ash layer. The geologist there is standing next to a tephra layer. The other thing is good about they stand out pretty clearly, so they're easy to find. Okay, now we're getting into some of the radiometric dating techniques. These are a lot harder to understand. So I'm
Real quick, if I could.
Yeah.
One of the other problems with relative dating is it creates a very shallow gene pool.
Get out of here, Watcher.
Fine joke, Watcher. Appreciate that. And you don't want to dive into that gene pool because you might break your neck. It's very shallow.
Yeah, so when I was trying to understand these, I'm going to basically try to give a basic overview of these, but a lot of them require, I'm looking at the papers that people are writing on this and they're using all these instruments that I don't understand how they work. And so we're just going to get a basic overview of this. So potassium-argon, this is one of the oldest, they don't usually use this one anymore, but the basic concept is a potassium isotope, which is K40. So this is a radioactive isotope of potassium. It decays into a stable version of argon, A40. Now, A40 is not the common isotope of argon, but it is a stable one. Okay. The A40, again, is trapped within the crystalline matrix of cooled lava. So what you're doing here, this is a relatively high temperature dating technique where you're basically dating the last time this rock was molten. Okay. Because what you're looking at is how much A40 is trapped within the crystals in this material. Obviously, the A40 won't be trapped in the material if it's not crystallized. You see what I'm saying? Mm-hmm. So this method counts the stable potassium, which is K39. That's the stable isotope of potassium. And then the argon, A40, in the sample to date the time of crystallization, or in other words, when it cooled. The range for it is approximately 100,000 years before present to 4.3 billion years before present, and the resolution is of roughly 1 million years. Okay, so it can date, the good point is that it can date very, very old things, but it doesn't have a very good resolution. But relative to 4 billion years, that's pretty good. But not when you're measuring 100,000 years, right? If you can't even, you don't even try because you got a resolution of 1 million years, you don't even try. But notice that what they call here is that we're talking about a daughter isotope, right? So the actual thing that's decaying is this potassium isotope called K40. What they're measuring is K39 and A40. Now, why are they doing that? It's because there's almost the amount of K40 is very little. And what they're doing is they're assuming, this is what's in the assumptions, the K40 is not measured, but it is assumed to be a constant fraction of the amount of K39. In other words, the isotopic...
They think they know the ratios.
The isotopic ratios of K39 to K40 are a constant. So all you have to do is measure the K39, which is much more abundant and easier to measure.
Do the math and you know what the K40 is.
And you know what the K40 was and at the time of crystallization, and then you can measure the A40 in the sample. And then with using all those numbers, you get an estimate of how long it's been and how much of that argon has been decayed from K40. Okay. So, and then contamination by atmospheric argon is common. So you have to, there's a contamination problem. Now, again, A40 is not common in the atmosphere, but it does get generated. Mm-hmm. Mostly in the atmosphere is A39, I think. Or maybe not. I can't remember what it is. 39 might be radioactive. But yeah. So this is a very old, they still use it, but not much. But this is one of the first radiometric dating types, potassium-argon.
Developed by pirates.
Now we go to argon. Argon. This was meant to replace potassium-argon, but this one's even more complicated and weird. So the first thing you have to do with this one is you have to irradiate a sample with neutrons. So you go find yourself a nuclear reactor and put your sample next to it. That's not actually what's happening, but you have to have a nuclear reactor, and you basically irradiate it with thermal neutrons coming from the nuclear reactor. Okay. So that converts the stable potassium in the sample, which is K39, into an unstable version of argon, which is A39.
AR39, yeah.
Yeah, AR39. A single count of argon isotopes allows the calculation of age once you've done that.
What do you mean a single count?
Like they can just hit it with a laser and do a single count of just the argon. They don't have to count two things.
Okay.
But the problem is, well, we'll get into that first. We'll get into this first. Range, roughly 20,000 years to, again, 4.5 billion years BP. Accuracy varies widely. And again, when I was reading the papers on this, they're all arguing with each other about how accurate it is and what the techniques you should use. And they would say things like, well, internally, we get a 0.25% accuracy, but that's a relative internal accuracy in terms of what they're doing with the nuclear reactor and how many neutrons they threw at it. That doesn't actually tell you what the accuracy is in terms of what the date of the object is. So the 0.25% that I was getting, I think, is about counting. An accuracy of counting.
Yeah. Because they may, the margin of error on the actual count.
But when I was looking at actual argon dates that were being given in papers, they were always plus or minus millions of years. So that's what I put. From 0.25%, because that might be the most accurate possibility, but most of the time they give the errors in millions of years.
Okay.
Plus or minus millions of years. Okay. So the pros of this technique is that it's technically much more simple than the potassium argon, because once you've irradiated it with neutrons, you just nail it with a laser and you're done. You just count. It's a one-time thing, and you can use a much smaller sample. The hard part is irradiating.
Yeah, if you're counting 4,500 things and your margin of error is a couple of things, that's pretty good.
Mm-hmm. That's right. Yeah.
So for the sake of argument, 0.25% of a billion is 25 million. So, 25 million years in error.
Yeah, 25 out of 1,000 things.
Yeah.
Meh.
So requires this is the weird part of it. This requires a simultaneous irradiation of a control sample of known age. In other words, you have to, when you're doing the neutron irradiation of your sample that you want to measure the age of, in order to know how many neutrons you threw at it, you've got to irradiate a control sample that you know how old it is in order to count that first. So that
what's
you can
their best known object?
Well, I think I was talking to one of the geology students in the Discord about this, and what I was reading about it is they use, for example, cooled lava from known volcanic eruptions.
Yeah,
right.
There you go.
So you get some Mount St. Helens lava, and you irradiate that along with the unknown sample, and then you can, because you know how old the Mount St. Helens is now. It's not that may not actually work because it's not very old. You probably want something older than that, right?
It'd be nice, yeah.
But all you have to do is turn potassium K39 in the sample into unstable argon, which will happen. There's plenty of potassium in there, right? Because what you want to do is you know how old this is, so you know all this stuff. So when you irradiate it, you can say, okay, this is how many neutrons got thrown at it. That means that's how many neutrons got thrown at this thing. Roughly.
Yeah, okay.
Okay, so now you know your neutron count, and then you can do the rest of the calculations by hitting it with a laser and counting the argon. It's just it seems weird, right? And I'm reading these papers where these physicists are arguing with each other over the processes, and it's hilarious.
Yeah.
And I searched all over the place, like what is the accuracy of this, and I couldn't find any definite numbers.
Yeah.
So I ended up having to look for argon dates given in papers, and they're always plus or minus millions of years. So I don't know. Calculations all involve assumptions of constant ratios between isotopes again.
And why is that? What gives them the idea that
Are constants?
the ratios between the isotopes are constant? Why
I
should that be?
I don't know. I didn't get into that. Maybe I should look into it. But it's a good question.
Correction, 2.5 million years. Sorry.
That's what I thought.
Oh, yeah, okay.
0.25% is going to be 2.5.
That's why I was saying, like, if you're looking for, okay, so yeah, a couple of things in 4,500 things is your,
Yeah.
I mean, I guess that would be more like a dozen things.
Fission track dating. I find this one fascinating. So uranium-238, which is a highly unstable version of uranium, fission decay damages surrounding crystal. So when you measure the total uranium content and then the track density in the crystal, the tracks are what is the damage, this can provide age since crystallization. So again, you're talking about dating a thermal event in the rock. The last time it cooled.
So you've got the formation of the crystal. The lattices are going to be, fairly pure, right? They're all connected.
a very tiny piece, and it can be like this pure piece of silica.
Yeah.
And you just measure how many times neutrons from the uranium-238 decay.
When they decay, they
burn a track through it.
the
Now, you
crystal,
can't see those tracks, but they chemically etch the crystal, and it enlarges those tracks into tubes that can be seen with a very powerful optical microscope.
Right. So they take it and they wear it down or erode it a little bit.
Yeah,
somehow.
so the tracks become more, chemically etch it. Yeah,
Yeah.
that's what they call it. So in some cases, to try to narrow it down
I wonder
more.
if this. I'm sorry, but we've talked about patina on the outside of these.
Oh yeah,
like flint rocks that we're finding. There's these,
it's probably track. Yeah, it's probably local radiation radon decay tracks. It causes damage to the crystals, and
there's so much damage that it changes the color of the crystal because it's now reflecting all this light.
It's no longer translucent. It becomes opaque. Yeah, exactly.
Cool.
So in some cases, to narrow this down to try to up the accuracy, they will again bombard it with neutrons, which causes the fission of the 235 that's present in the material. Those tracks are recorded on a thin plastic film. Then that is counted and compared to the spontaneous tracks that happen in nature. This is one of the ways they count, because again, we're looking at isotope ratios. They count the 235 to figure out how much 238 was in there, because 235 is stable. But if you bombard it with neutrons, it will cause fission. The tracks on that will allow you to count that 235, which allows you to figure out how much 238 there was, and that helps you count the tracks.
Because you're assuming the ratios are.
That's right. So they bombard again. They go to a nuclear reactor, stick it next to a nuclear reactor, and put a little thin, put a piece of tape on it, but a thin plastic film. Right. The neutrons coming through hit the 235, cause it to fission, and it causes tracks in the thin plastic film. Then you etch those and count both.
I'm going to make an assumption right now that a lot of these assumptions about these ratios come from the development of nuclear material, right? Like when they were developing the nuclear bomb.
Yeah.
There's all these physicists and they're doing all this math and they're trying to figure out all this stuff, and they're like, okay, these ratios should be like this. And so when we try to enrich this thing, we should expect to detect this much decay and blah 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 from these elements, and margin
they would refine it over time,
and they'd work on it, and then they'd find out, okay, it's a little different. Why?
Yeah.
And then they dive into that and try to figure out why. Oh, it's because there's the presence of this other thing that's and that's why it's causing that to happen. You see what I'm saying? Like,
yes.
I bet you that's where these assumptions come from. Because and so ultimately, what I'm saying is, through the process of experimentation and repeating these experiments and getting similar results and being able to build things based on these assumptions, they're pretty solid. Not in every case.
Right, the difference to me is that, are these things constant over large periods of time?
Right, yeah.
That's the problem. Sure. Right now, yes, your ratios, but we're measuring things, and in some cases are billions of years old. I mean, was that isotope ratio actually the same back then around here? I mean, I don't know. Maybe they were. But we'll get into that later when I do talk about some of this and the idea of radioactive decay in the first place and why it can be considered a constant, because this is another assumption. I haven't even mentioned it, but another assumption here is that the radioactive decay is a constant.
Right.
Okay. So the range of fission track dating is roughly 100,000 years to 2 billion years before present, and I couldn't find a margin of error. Nowhere.
Wow.
Assumptions and problems. Measuring the total uranium content relies on isotope ratios being constant, because again, they're measuring 235 to figure out what the 238 was. Because you got to know the 238 and how much, you got to know that when you look at because you can count the fission tracks, but you need to know how much 238 it started with.
Right.
So here's a picture. That's a very small sample, but you can see these are chemically etched fission tracks in that piece of crystal.
Wow. That's cool.
And you can see they're basically homogeneous in all directions. They're going everywhere.
Really cool.
Yeah. Okay. So, other types of radiometric dating that we're not going to go into super detail about, but these are ones that exist. Uranium lead. This one ranges in hundreds of millions to billions of years, and the margins of error are over 2 million years. I don't even know how to say this. Samarium neodymium. Accuracy of within 20 million years and ages of 2.5 billion years. Rubidium strontium. Error of 30 to 50 million years per 3 billion years. And uranium thorium ranges within hundreds of thousands of years, and I couldn't find a good margin of error for this one either. Another one that's supposed to be better but can only be used on a very small amount of material is uranium thorium helium, where they count all three of those things or daughters of those things and use all those numbers to add up a whole bunch of stuff and divide by things. It's all of this is in most of this, they're not actually counting the things doing the decaying. They're looking at
They're
looking at daughter particles or whatever. Yeah.
Yeah, because the things that are doing the decaying are gone or whatever.
Yeah, and you need some isotopic
Something
ratio
that's more stable to figure out and what the ratio was, so that you can know what the starting point.
Yeah, and then you have to assume that the ratio has been constant throughout all of time,
Especially,
which it definitely hasn't.
Yeah, billions of years ago.
Yeah. We know the universe evolves. It started out with nothing but hydrogen, right?
Yeah, so the ratios between two different isotopes of whatever
were not the same then as they are now.
It's a good point.
Okay, so now we're going to the universal law of radioactive decay. This is the final slide here.
Oh, wow, you're actually going to do this. Look, the sands of time are almost out.
We have Discord questions too, so we're not going to do it.
Okay,
so the universal law of radioactive decay depends on the assumption that the nucleus of an atom does not age. This is how they actually phrased it when I was reading about this. The nucleus of an atom does not age. Therefore, the passage of time does not increase the probability of decay. The probability, therefore, remains constant. In other words, as time passes, the probability that it will or will not decay remains the same no matter what. Because in their minds, the nucleus of an atom has no way to experience time. It doesn't age. This is an interesting way to phrase it.
That's cool.
So according to them, once you've figured out the half-life, roughly, it's going to be the same for every kind of that same isotope. Because it doesn't matter if that isotope has been around for 1 billion years and hasn't decayed yet, its half-life is the same thing. The probability that it will decay or not is still the same no matter how old it is. It's weird. So you can give it a half-life because you're looking at large, very, very large numbers of them. And that tells you that, for example, C14, over 5,000 years, roughly half the C14 contained in some amount will have decayed. But you can't point to any individual one of them and say it will decay or not.
Yes.
And the fact that
this is this very similar to nucleation. It's so weird.
Yeah.
I don't know. It seems similarities. Nucleation meaning like a nucleation site for crystal formation.
Yeah.
There's it's going to form somewhere, but there's no way to tell when it's going to happen or where.
Yeah.
There's no way to look at any individual atom and decide what's the probability that this will become the nucleation site,
Yeah.
and when? There's just but you can take a mass, like a group of however many. I don't know what the counting is in terms of the atoms when you got this soup of this specific element you're wanting to crystallize, and you can say, well, it should start in this amount of time, right?
Yeah.
And then it will.
Yeah. Somewhere.
Somewhere in there.
Yeah. Right.
It's so
And
weird.
what's weird about it is the half-lives are half-lives no matter what. At any time you look at it in the system, the half-life remains the same number.
Yeah.
So
Well, you can't have a half-life with a single object, right?
No. Yeah.
A
So
single
in
thing.
a system of C14 or a sample that contains C14 in 5,000 years, half
Half
of
of it will
C14
be
will
gone.
have decayed. But when you look at it at that point, you're like, all right, half of it's decayed. Well, guess what? Half of what's left will decay in another 5,000 years. The half-life remains the same.
Yep. Should we tell the half-life joke?
What's that?
An infinite amount of mathematicians walk into a bar.
Oh, yeah.
And the first one says, give me a beer. And the second one says, give me half a beer. And the third one says, give me half of that beer. And the fourth one, and the bartender's like, Jesus Christ, here's 2 beers.
Yeah, it's going to take forever. Here's 2 beers.
Yeah, that's right. That's going to take forever. Here's 2 beers. That's what it is. Screwed up the punchline. Threw Jesus Christ in there.
So all radiometric dating techniques, whether it's cosmogenic or not, in other words, whether it's cosmogenically generated radioactive particles or just things like uranium, they all rely on this assumption of the universal law of radioactive decay. So this one's not a fact, but a question. Are there other conditions? Because I don't actually want to argue with this. I think this is... Yeah, I wouldn't argue that the nucleus of an atom ages, right? But this might be a similar I was thinking this might be similar to the thing with mass and gravity. They're talking about the wrong thing there. I don't want to know if the atom ages. What I want to know is, are there other conditions that can change the decay constant aside from the passage of time? In other words, proximity to a star, for example, or changing stellar processes. There is some evidence, I remember reading this somewhere, that it's possible that the constant of radioactive decay is dependent on where you are in terms of near any stellar objects. And if you're farther away from them, it may be less or more. Or if the star itself is doing something interesting and changes what it's doing, and a whole bunch of its properties change, that radioactive decay may take place differently in the vicinity of that star. And this is something that you can't really test.
Right. Or it's like
We can't test it yet.
the atom does not age, but maybe it does in terms of like the progression of whatever the universe as a whole is doing.
Yeah.
So that
could
you
be
can't tell the age of an atom based on any other atom because they're all going to be basically the same.
Yes.
But if you go back to the early universe, they were all the same in a different way than they are today.
Yeah.
That's why you just can't measure it against anything else.
That's right. Yeah. So is the universal law of radioactive decay actually a universal law, and is it a constant, is the question.
Yeah.
I would say that probably for carbon dating, the decay is probably constant. Within the past 60,000 years, has it changed much? Well, maybe if Robert Schoch is right, and the last thing that happened, the last destruction of the planet was about enormous solar activity, it's possible that may change decay rates.
Well, I think that's actually been shown to be true, right? Because right around that period, the Younger Dryas period, is like the carbon dating gets messy.
Yeah, and that might be because of, but remember that's based on cosmogenic nuclides. So that could be because there were more cosmic rays, or it could be because there was more nitrogen, or it could be because the decay was changed, or it could be part of or a mix of all three.
Of all, yeah.
Yeah. So that's it. That is that presentation.
That's great.
And okay,
Yeah, I'm gonna have to. Damn, I'm gonna have to watch this again. Well, I'll try listening to it. Maybe I won't need to watch it again.
Damn, I'm gonna have to watch it again.
I ain't got time to watch it.
Oh yeah, some Discord questions here, and these are really good. Okay, first one was asked by Janus, and he said, "What do the 0.01% of cosmic rays that are antimatter tell us about the symmetry and distribution of matter?" And when I was looking into this, and I don't have a good answer for this, and I don't think anybody does. But as far as I could tell, the cosmic rays that are coming in that are antimatter are mostly positrons. If there are heavier, massy particles that are antimatter, I'm not aware of it. I don't think they've found any, like, for example, anti-helium nuclei.
I wonder if he's talking about sort of the dark matter thing again, because like when you look out at these massive structures and you imagine that how many cosmic rays over how much time have passed through that structure and annihilated other matter.
Yeah.
And so you have a structure that appears by the light in our calculations of the mass to be in this organized form, and then the calculations come out all wrong.
Yeah.
Well, how much matter has been annihilated? Like, in other words, I don't know if that's what he's getting at, but like the formation of this antimatter ultimately annihilates with matter.
Yeah. But nevertheless, there is a tiny, tiny percentage of cosmic rays that are incoming that have been detected as being antimatter, which is really interesting. Where are they coming from? Now, we know that stellar processes, we were looking at this, the hydrogen...
Or is the antimatter... Well, never mind. Sorry.
We know that stellar processes, the proton-proton chain or whatever, in some cases, they generate positrons, which is an antimatter particle of an electron. But it probably almost immediately annihilates. But when the star explodes, there are going to be positrons that haven't been annihilated yet that might be kicked out by and become a cosmic ray. And then they can go burning through the universe, and if they're really lucky and they don't touch anything until they hit our atmosphere, it's going to be an antimatter particle coming into our atmosphere, and it'll annihilate immediately when it comes in. Not only does it have all this kinetic energy, but it's also antimatter, right? So one of the things that astronomers were trying to do with this question, because they noticed, like, wow, some of these cosmic rays are antimatter.
But how much energy is released in a matter-antimatter collision?
All of it.
But it's...
It's total energy conversion.
Okay.
So basically you take that E equals mc squared and you take all the mass and turn it into, energy.
Right. Okay. Yeah. I was thinking about... I wasn't thinking about conservation of energy. I was thinking almost like you would... say dampen, or not dampen, but attenuate sound by the opposite polarity of waves. So
yeah. They
right?
might cancel each other out.
Yeah.
Yeah, they do, but they make this horrendous noise, I guess you would put it in those terms.
Yeah, because you're not destroying energy. And
Right.
both of the things are energetic.
Yeah.
Even though they're just made in opposite ways.
Right. And whatever tiny amount of mass they have is instantly converted into energy.
So it's a lot.
Yeah.
Yeah, okay.
So the interesting question about this, though, is that astronomers noticed that some tiny fraction of the infalling cosmic rays towards the Earth were antimatter. And then the question became, are there islands of antimatter out there in the universe that are generating these things? And now you have that, I can't remember what it's called. It's called the baryonic, I don't know what the term is. It's something like that about baryons. Radiometric problem. It's one of the biggest unsolved problems in physics aside from dark matter and dark energy, which is why was there more matter than antimatter created in the Big Bang?
Yeah.
So the question is are there big antimatter islands out there in the universe, they would have to be isolated from the rest of the matter. That was why they were called an island. They're isolated.
Or are we just inside of a primordial black hole?
Yeah, it could be that too. Yeah. But recent studies have shown that it's possible that most of the antimatter, the positrons that are coming in that are cosmic rays, are actually being generated by nearby pulsars. So I don't know. This is all new stuff. So I don't know, Janus. This is a great question. But yeah, does it tell us about distribution? I don't know. I think they were trying to ask that question, and I think that right now they're thinking maybe they're coming from very fast pulsars, very highly energetic ones. And
man, once again, the Feynman book, The Character of Physical Law, has some really cool stuff about antimatter in there. Like his description of it's cool.
Cool.
Very good. We got to go through that book one of these days.
Yeah, we'll have to go
on the
through
podcast.
All right. Another question was, what are the current techniques for dating stones, or what's the progress on being able to date them? So I think we went over that in the presentation.
Mm-hmm.
A lot of these methods we were talking about are for dating rock specifically. But specifically archaeologically, they like the luminescent stuff.
Yeah, and they choose the dating methods based on
how old they think it is.
Already, yeah, their assumptions are.
Yeah. And also what they're trying to find.
And what you're trying to find, because you're not going to use, let's not find out when the last time the rock was molten.
Yeah.
Right? And they should do that with like Sacsayhuaman or whatever.
Yeah. Maybe they should, yeah. Yeah. Yeah, last time it crystallized. Yeah.
Yeah. But typically in an archaeological setting, you're not going to do that.
That's right. Yeah.
You're going to look for the last time it was exposed to light.
Yeah. In an attempt to date the structure.
Right.
Yeah. And that may just tell you the last time the structure was refurbished. That's another problem.
Because it could have been just piles of rock that fell
somebody
down and
rebuild.
just rebuild it.
Yeah, exactly. Okay. Black Shaman.
But if it was built in the middle of the night in a fit of rage, it was not reset.
That's right. He says that the initial Big Bang process took place in a matter of minutes, and that's when all the lighter elements were created. My question is, if this process had taken longer, would the conditions be right for different elements to be classified as lighter elements? And if so, would that then create different conditions for life? I think they refer to them as light elements because of their atomic mass. So yeah, probably if the process, the initial Big Bang process that created all the hydrogen and most of the helium had lasted longer, it might have created more heavier elements, but they wouldn't have been called lighter elements necessarily. I mean, they would have been on the light end because the really heavy elements require lots of fusion to take place first. But yeah, the longer that process goes, the heavier the elements you get. But I don't think that they would refer to the heavier elements then as lighter ones, because what they're talking about when they talk about lighter elements is the atomic mass. So I hope that answers the question. And again, remember,
they're breaking it into billiard balls, so you're looking at, like how many of the same thing. Essentially, like the one proton thing is a hydrogen, right?
Yeah.
So you clump a bunch of those together, and then you get other things. But it's all I don't know. It's weird. It's like building blocks.
Yeah, but he was just saying,
if you put 4 or 5 bricks together, do you call it a brick? Or is it a wall?
Yeah. Okay. That's a good point. Yeah. I think what he was saying is if the Big Bang process lasted longer, all the hydrogen would have been turned into heavier stuff, and then that would have been referred to as the lightest element in the universe.
Yeah.
Possibly. Yeah. I don't think it would have used up all the hydrogen. But maybe. I don't know.
But through the other processes, we would still have hydrogen.
Yeah,
through later process, it would go break back down.
Yes,
and
that's
so
right.
Whether or not it happened at the very beginning of the Big Bang, you'd still have the lighter elements later. And
yeah, that's the difference between fission and fusion, by the way. Fusion stacks two things together to make a bigger thing. Fission breaks a big thing apart into smaller things.
Okay.
Yeah. So the first nuclear bombs were fission bombs. Our nuclear plants are fission plants. We haven't built a fusion plant yet, but they have built hydrogen fusion bombs that are set off by fission reactions that are set off by a chemical reaction. Okay, Pete asks, how long does each dating process take to do and roughly the cost to do it? Man, those are great questions, and I did not even look at that. But I can say that the luminescence stuff, and in some cases, if you ignore the fact that you need a nuclear reactor, the argon-argon process is cheaper.
Yeah, I would say that the nuclear reactor time is very expensive.
Yeah. And when you need, accelerator mass spectrometry, which is what you need for carbon dating, is an expensive deal. You've got to have a nice lab. I showed a picture of it. You've got to have a pretty good, very expensive setup. And then you got to have people who know what they're doing.
You don't have to necessarily pay for the lab, but you have to pay for time in the lab.
Yeah.
Right.
Yeah,
Once the lab is built, people are hiring it to do all kinds of stuff. So
that's right.
It depends on the demand of that lab's time.
Yep.
We'll set their prices.
But how long does each process take? That's a great question. I don't really know. But I know that some of these processes are very expensive, and how long they take is starting from sample collection all the way up until the final, whatever the processes are to date, can take, it could take years. It just depends on what's going on. Hopefully it won't take years, but you may have to stand in line to get your sample dated. So... but he says, I feel like that has a lot to do with certain sites. There is no money to put towards further research on certain sites, already dated by older techniques, and then dates set in stone by the mainstream. Also, what is the accuracy of each method? So I think I went through the accuracies as best as I could in the presentation. But yeah, it's a great question. How long does it take, and what is it? Man, some of these numbers on this stuff is hard to find. I'm like, I could not find the margin of error for some of these techniques. It's so weird. Bud Flapperton. He wants to know, is there historical data on cosmic rays, and do we know if the levels have fluctuated in the past? Yes and yes. There is historical data. The first way they measured them was by proxy, basically. You could see the gamma rays they made when they hit other planets' atmospheres and ours. And now they have direct measuring instruments that they've put up on satellite probes, and they've got one on the space station. I don't know if it's still working, but it weighs like 7.5 tons, and they moved it up there, and it's got all these interesting magnets, and it uses the same kind of particle detectors that are used in accelerators. So don't ask me how those work, but it has one of those in it. So it can detect the particle coming in, and then it uses all these magnets it's got in there to find out what kind of cosmic ray is it? Is it just an electron? Is it a positron? Is it an alpha particle? Is it just a proton? And it can sort of sort them right when they're coming in. Really cool.
Aren't they also doing this in Antarctica with the balloons and stuff?
Yes, they've done cosmic ray detection with balloons too, but those are still in the atmosphere, and it's already down the chain. So up in space.
But that's where they put the balloon up there, and then they started detecting stuff coming out.
Yeah, they're like, wait, cosmic rays coming out of the planet.
There must be a universe that's completely backwards from ours.
And yeah, levels have fluctuated in the past, and that's shown in the tree ring dating. But there's other possibilities of what that fluctuation is. But because, and this is the other thing, when I was looking at cosmic rays, they still aren't really sure what the sources are. When they first were looking at cosmic rays, they seemed to be coming from every direction equally. Right? So you put out a detector, and that detector would detect cosmic rays coming at it from every possible direction in equal amounts. There was they didn't seem to originate more from this area than that area. You see what I mean? But more recently, with more sensitive detectors, they have found areas where there seems to be more coming from that particular area than elsewhere, but they still are mostly coming from everywhere. And that may just be a function of the size of the universe.
Yeah.
And, the universe is so big and also so old that cosmic rays are hitting our planet that were generated by things that happened billions and billions and billions of years ago, and it's been traveling here ever since at 99.99999% of the speed of light, which is not very fast. Right? It's going to take it a lot longer to get here than the light that was generated by that energetic thing that generated that cosmic ray. Because that light has that one little 0.00001% of C on that cosmic ray, and it's going to get here faster. And if it was billions and billions of years away, it will get here millions and millions and millions of years before that cosmic ray does.
Mind-bending shit.
Okay. And last question. How are cosmic rays detected, and what is used to detect them? Yeah, so I sort of answered that Kyle said balloons, which is correct. They were first detected using the reactions they make in the upper atmosphere, by looking at gamma rays. And now they do very sophisticated particle accelerator type detectors up in space. So, anything else? What am I forgetting?
I don't know.
I don't
It's been a load of information. I'll tell you that. But yeah, that was cool.
Hey,
So
we have 2 watchers in here. Look at that.
Oh wow. There's no way of really knowing how long this show has gone on.
That's right.
It's basically what it seems like to me. It's a lot like how fast are we moving? You have to compare it to this thing, and then compare that thing to this other thing, and then compare this thing, and just.
I'm sure I'm forgetting. I feel like I'm forgetting something. I'll remember.
There's
next
no
week.
edges of the box to measure from.
Yeah, that's right. There's no absolute point.
Yeah.
So I guess all I'll say in closing is that all of that was standard model, but I find it important to understand that model because so much of how we talk about these things that we study, like pyramids, is couched in standard model terms, using standard model dating techniques, using standard model theories on how the universe works in physics.
And we're about to do a deep dive into a book,
That's
which
right.
is going to be talking about all these dating methods, and so now we have a better understanding of the whole.
Yeah, now that everyone is thoroughly confused, we'll go into the book.
That's right. But I mean, just considering the margin of error in so many of these things, and the assumptions that that are part of it.
Yeah. All right. Well, I hope you guys enjoyed that. You guys can get a hold of us, brothersoftheserpent@gmail.com. Check out the website, brothersoftheserpent.com, for everything snaky. All the cool stuff is on the website. Join the Pyramid Scheme by supporting us through Patreon or through PayPal. And thanks so much to everybody who has done that. We really appreciate it. You got any Patreon messages? You got any PayPal messages?
I haven't seen it.
Okay.
I have been looking. I have been checking.
He's been paying attention. Hey, look at those.
These are beautiful.
Danglies.
I peeked in here earlier when we opened the package, but man, these earrings are awesome. Thanks, Birch.
Yeah. Give us reviews. That really helps share the show. Thank you so much to all of you who have done that. But yeah, just go to Apple Podcasts and give us 5 stars, no matter what you say. You can say that we suck, but give us 5 stars.
That's right.
And join the Discord. And a couple of words about that. It's real simple. If you want to join the Discord, hop on our website and go to the Discord chat section of the website and click the connect button on the little widget. If you can't figure out how to find it, it's probably because you're looking at the website on your mobile and you're looking at the mobile version of the website, which I hate, but I put it on there because people like it. So either switch it to the desktop version or go to the bottom where the menu is and you can find the Discord chat, click on the little button and you'll hop in. And if you want to have notifications of things, like, for example, when we're going to do a live to the Discord show, if you have the mobile app, it's way better than if you're just joining the Discord on your computer. Because if you're joining on your computer, you can talk to people, but you don't get the notifications like you do with your phone. So if you're walking around somewhere and Kyle and I decide, well, let's do a live show today, we'll send out a message that notifies everybody in the Discord. And if you have the app on your phone and you're in our server, it'll notify you, hey, everyone, we're going to be doing a live to the Discord today. So if you're only using it on your computer, you won't get those most of the time. Or you won't see them until it's too late, unless you happen to log in before we do the show. So yeah, join the Discord chat. That was set up and it's run by Jeff. Thanks very much to him. He also runs the Library of the Serpent. Thanks to History Shift for making all of our YouTube videos and keeping track of our YouTube stuff. Man, it's been a huge help.
Thank you, buddy.
Yeah, less work for us, which is exactly what we're after here. That's the goal. Thanks to Pod Doodles. Don't forget about Cosmographia, the podcast we do with Randall Carlson. And we love you guys.
Always have.
Always will.
Good night, Adamu.
Get back to work.
And thanks for that presentation, buddy.
Hey, man, no problem. Never again.
I took the speed of a baseball bat, set the ratio for the surface area diameter, basically, or width at the front edge of a bat, created a ratio equal to 20 inches, which is the width of the standard queen pillow. Then took a ratio of the weight and modified the speed using both of those, which comes out to about 35 miles an hour, by the way. And then took that times the mass to get the number of newtons, and the equivalent rate of travel of an alpha particle would be 124 octillion miles an hour. Yeah, so that's how fast an alpha particle has to move to have the energy equivalent to getting smacked in the face with a pillow swung by a baseball player.